Hey everyone, this is Aanshul Sadaria, software engineer at Google. Now, in one of my previous system design videos, I talked about a very important concept of caching for horizontal scaling. In this video also, I'm going to cover one such important concept for horizontal scaling, which is sharding. But before we dive deep into the topic, don't forget to check out Scalar's free masterclasses taken by industry-leading experts only on Scalar's event page. Link is in the description below. Now, let's get sharding. Now, are you ready? I know you might be worried that I will start with a theoretical definition and bombard you with lots of technical jargon that you might not be able to understand. But let me start with a real-life analogy inspired from my own experiences to explain what sharding actually is. So, when I was in college, we used to have few midterm exams, we had one end term exam as well. Now, the sitting arrangement of my classroom was something like this. There were 4 to 5 columns of desks. There was one table over here, and behind the table was the blackboard. Now, after the exams were over, the professor used to share our answer sheets with us to check the marks and whatnot. So in the first couple of semesters, what he did was, it was a class of 200-250 students. So what he did was, he would pile up all the papers on the table itself. Okay. And what happened was, the entire crowd of 200-250 students used to gather around the table, and it used to take a lot of time to identify their paper, check it, and then place it back on the table. Now, what happened in the next, after a couple of semesters, he changed the strategy. What he did was, instead of putting all the papers on the table, he started keeping it on the first desk of each column. So what he did was, he kept a bunch of paper from roll number 1 to 40 over here. He kept 1 to 40 over here. Then 41 to 80. Let's assume the class was 200 strength big. So 81 to 120. 121 to 160, and the last batch of 161 to 200. Now, instead of all the students gathering around the table, what they did was, they were bifurcated in different columns of the desks, and the process became so streamlined that it was very quick to check the papers and place them back. Now, this is similar to what sharding actually does. I'm not sure if this analogy was the best analogy or not, but when there are lots of concurrent requests coming to your server, it is possible that the capacity of the server is not feasible or suitable to handle that request. Okay, so let's assume that there is a server over here. Okay, let's forget the classroom example. Now, there is a server over here, and it is getting bombarded with lots of concurrent requests. Now, every server has some capacity, it has some RAM, it has some disk capacity, it has some network bandwidth as well. Okay, so these are all resource constraints, like RAM is there, disk capacity is there, and network bandwidth, and lots of other things are there. Now, these all resources are limited. So once your system or your product starts receiving more users, starts acquiring more users, the number of requests is bound to increase, and number of concurrent requests will also increase. So your server might not be able to handle such high load of request. So what we do is, instead of a single server and a single database obviously sitting behind the server, now there will be one database sitting behind the server as well. So instead of this architecture, we break the database into multiple machines or cluster of machines. Okay, now let me just get rid of our classroom example. So now, instead of one server and one database, we break the database into multiple databases. So instead of 1 DB earlier, let's say for the time being, we break it down into 4 databases. And we partition the data in the databases in such a way that no row is repeated in any of the databases. For example, if there was a row 1, let's say row 1, row 2, and row 3. Now, if row 1 lies in 1 DB, it is not going to lie in any of the other DBs. Okay, and now each of these machines in which we have partitioned our database, each of these machines is known as a shard, and this concept is known as sharding. Okay, so each of these new servers, each of these new databases, these are shards. All right. So we have understood the theoretical definition of what sharding is. Now let's move to a very naive example, and I will run through how sharding actually happens in like real systems. So this is just a hypothetical example, like there are 6 columns and this is a user table. Okay. Now I have just added a few names randomly, like Anshul, John, Sam, Raj, Christina and Carol, and these are all hypothetical emails. Okay, so don't try to email me on anshul@email.com. It won't work. So in sharding, we break the database. Let's say for this particular example, I will break it into 2 shards or 2 databases. Okay. Now it depends how you want to partition the data. In my use case, what I will do is, let's say A to H. Okay. Now all the names which start between A and H, will keep them in one shard and the other names will go in the second shard. So A to H is our first shard and I to Z is our second shard. So let's see what all data is in our first shard. Now Anshul will come in first shard. So this is user ID 1. I'm not repeating the entire example, Anshul@email.com and so on. But let's assume that it is going to be there. Okay. Now John will be in which database? Okay, it should be in the second database or the second shard. Now this is user ID 2. Sam will be in the second shard as well. Raj will also be in the second shard. Now these are all user IDs, just to remind you all. Okay, and Christina will come in the first shard. So the user ID is 5 and Carol should come in the second shard. So this will be user ID 6. Now we have sharded our original database into multiple shards. In this case, we are using only 2 shards. We can have 3 shards, 4 shards, depending on how much finer we want to divide or partition our database. Okay. Now hence, like since there are only 6 rows in our table, it is fine to start with an example of 2 shards. Now there is a routing server which tells the request which shard to get the response from. Okay, routing server or lookup server. So there are 2 servers sitting in front of both of these databases based on the shards. So let's say this is S1 server 1 and S2. Okay, now there will be one lookup server or master server. You can call it any name. It doesn't matter a lot for this technical explanation. So this is a lookup server. And let's say we want to add some new data. Okay, let's say there is another person with the name of Rohan, for example. Okay, so now when we want to add this particular row in the database, we will ask the lookup server, hey, my name is Rohan and my email ID is this XYZ, rohan@gmail.com, for example. Which shard should I write the data to? Okay, so Rohan request comes and there is some email ID. We don't care about it. So now the lookup server says that, hey, your name starts with R, like your name is Rohan, it starts with R. So for shard 1, your name should start with A to H, which is not in this case. For shard 2, your name starts from A to Z, which is in this case. So we will add Rohan to shard 2. Okay. And this will be user ID 7. We are just incrementally updating it. Now let's say there is a read request for from the database server. Okay. So the read request is for, let's say, Christina. Okay, so now Rohan was a write request and read request is for Christina. Now the request again asks the lookup server that, hey, I'm looking for a user with name Christina. Which shard should I fetch the data from? So the lookup server would be like that, since the name starts with C, it would be lying. Okay, it would be present in shard 1 because like the range is A to H. So it will get the data, which is user ID 5 in this case, and it will return to the user. So this is how sharding happens in real systems. I mean, this is a very naive example. The real systems, the sharding logic will be much more complicated. It won't be A to H and I to Z and such normal examples, normal approaches. So it will be much more complicated. The databases would be quite huge in the range of millions, billions, and even trillions if they are done by systems like Amazon, if it's an order table. Okay, I don't know how many orders have taken place in Amazon till now, but I would expect it to be in the range of trillions, if not zillions and so on. So this is a naive example of sharding, and I hope at this point you understood from the real life analogy as well as the actual example what sharding actually is and why do we do it. It is to increase the capacity of the system to handle more requests as your product goes further. Now it is important to understand, okay, first of all let's get rid of all of these jargon. Now it's important to understand why sharding is important, what are the advantages, and now you must be thinking that since sharding helps to improve the capacity of the server and improves the performance and all of that, all the gold is gold, but that's not the case. All the gold is not gold. Like there are some disadvantages to sharding as well, and we should keep in mind what particular use case we are having and then decide that whether sharding is feasible or not and what approach of sharding we should take. In this case, we used an approach of names, for example, the first letter of the name. We can also use the approach of user ID. Okay, let's say user ID modulo 2 in this case. Okay, since there are 2 shards. If there are 3 shards, 4 shards and so on, we could have some sort of a function wherein there would be some entity. Okay, now I forgot to explain one important part over here. Since we divided our database into multiple shards based on the column name. Okay, now this is what we use to bifurcate our data into multiple shards. This is known as shard key. Okay, this shard key is responsible for writes and reads, which shard to write in and which shard to read from. Now there could be a different approach wherein our shard key was user ID, and we could use a modulo operator or any hash function or any function whatsoever. We could just pass the shard key into the function, and based on the result we will try to write or read from the respective shard. Now as I told you, it's important to understand the advantages. Obviously, like there are a few advantages of sharding. On the other hand, all the glitters is not gold, so we will need to understand the disadvantages as well. And there are different approaches of sharding which we will cover in detail, like what all are the different types of sharding, what all are the different algorithms. So these 3 sections is going to be the limelight of this particular module, this particular tutorial, and ultimately I don't want you to be bored with all of these theoretical discussions. We are going to talk about some real systems and how sharding has worked well for them and how sharding backfired for them as well. So lastly, we will cover some case studies of real systems. I'm not going to reveal which systems we are going to cover, but yeah, hope you are hooked to it. Now let's first start with the advantages. The first advantage is obviously scalability, which we have talked a lot while I was explaining what sharding is. So as I told earlier, as let's say this is your server, okay, the original server before sharding. Now this has a RAM of 8 GB. 8 GB is quite common and normal nowadays. We have 1 TB disk capacity. And there is some network bandwidth. Now, let's say you are an upcoming startup. You start with a very simple server, a bare metal server, which is able to handle the normal capacity right now. But let's say you got some seed funding and you started acquiring more users, and your user base has grown double, triple, and possibly 10x, 100x. Okay, 100x in 1 year. So your simple server might not be able to handle such a request. So as I told you earlier, we will distribute our database. Let's say it went up till 1 billion. Okay, now your server is not able to handle that request. So we'll distribute it among a number of shards. Let's say there are 100 such shards. Okay, there are 100 such shards. Now all of them have 8 GB RAM. Okay, I don't know the actual RAM capacity, but we are taking an example. So 8 GB RAM is present with all our new shards and new servers. All of them have 1 TB disk, all of them have some network bandwidth. So we multiplied the capacity of our server. Now, since our user base has also grown by 100 times, now we are at a better position to handle the new request with the new traffic, and the system resources are also not constrained. We are able to improve the user experience, the latencies have dropped down, and our system is working fine. So scalability is one important, all the efforts which we are doing, caching, sharding and all of that, the ultimate purpose is scalability. There will be some byproducts of this, there will be some advantages, which is not the main motivation behind why we are doing caching and sharding. If you remember what concept we are trying to cover, it's horizontal scaling. Okay, so scalability comes as along with it. So these are all top techniques of horizontal scaling. So scalability is the main, motivation behind this. Now there are some other advantages to doing sharding. Okay. Now one such advantage is high availability. Now what do I mean by availability? You must have used like services like Amazon, YouTube, and so on. Like you can't live without all of these services, WhatsApp, Instagram, and all of these apps. Now, what is one thing which is common in all of these applications? They have super high availability. I don't remember a time when YouTube was down for a few hours or maybe a day. I have not heard it at all, So all of these applications boast, or they are proud about their availability, which would be in the range of 99.9999%. Which means that within a few years, they would be down for a few minutes or at max a few hours. They cannot bear downtime more than that. Okay, if you remember in one of the news when Google was down for a few hours, it incurred a cost of a few $1 billion. So now this is the risk of having a normal downtime like a few hours. Okay, so these systems need to have high availability. Now let's understand how does sharding fit into this entire picture. Okay, earlier, like if you remember, it was just a simple server, one database, and all the requests were coming to this single server. Now it can happen due to any of the reasons, okay, natural calamity, or there is a power disruption in the entire city or whatnot. Okay, I don't want to highlight what reason it is, but a server can go down. Now, if there is only a single server and the server goes down, the capacity to handle all the requests goes away. Okay, your server is down, your product stops, and you start incurring cost, which is in the range of billions of dollars if you are a big company like Amazon, YouTube, WhatsApp, Instagram, and so on. Now, what happens with sharding is that you obviously have a lot more servers now. You have a lot more databases. And an interesting part about real use cases is that these shards are geographically divided. Okay, it can be in the same location. For example, like I'm in Bangalore right now. So it is possible that for a Bangalore-based startup, all the shards might be in a single data center itself. But for such huge applications like Amazon and so on, the shards are usually divided into multiple geographies. Now, we know if there is one server and it goes down by any error, your product goes down. But now, since there are multiple servers now, okay, if one of the server goes down, let's say the server 1 went down, server 2, 3, and 4, they are still up. So for example, if there is a request, okay, if we remember the previous example of user table, so there is a request like, hey, give me all the email IDs so that I can send a newsletter to them. Okay, let's assume that the database that we were building, okay, user table, this is meant for a newsletter service. Now there might be a use case that, hey, give me all the emails so that I can send this article to all of these people. Now, if one shard is down, okay, let me just name these shards as well. Now this is shard 1, shard 2, shard 3, and shard 4. Now if one of the shards is down, what will happen? The lookup server will be like, okay, it doesn't matter. I will send my request to shard 1, it will be denied. I will send my request to shard 2, it will return me all the emails, and same for shard 3 and shard 4. Now, even though shard 1 is down, we are able to get the email IDs from the other shards and are able to send the newsletters to a few people. Obviously, 100% accuracy of the data won't be there since the server is down, but our system would still be running. Okay, the requests which are coming to shard 1 might be redirected to the other shards. Okay, and then our system is still able to cater a part of the audience or cater some part of the data to the client. So this is a very big advantage for the tech giants, for an upcoming startup which is going to face a lot more users. They are going to incur a lot more concurrent requests. So high availability is a very big plus. Now I will talk about this, like when I talk about some of the disadvantages, when I talk about some of the use cases, I will talk about why high availability is so important. But remember this, we talked about two advantages. Scalability is obviously the main motivation, but high availability is a big byproduct of this technique. Now the third advantage is improved read response time. Okay. Now, before I bombard you with some more technical jargons, let me just reiterate on our example. Our database has, let's say, 1 trillion rows inside it. Like in the database, there is a table which has 1 trillion rows. Now, this is, let's say, it's a product table or an orders table from Amazon. Okay, so this is the database, and in that there are 1 trillion rows in it. Now 1 trillion would be, billion is 10 raised to 9, so trillion would be 10 raised to 12 rows. Okay, now this is a massive database, and in order to, like, if you want to fetch the orders placed by a user, you need to go through this 10 to the power 12 entries and then return what all orders were placed by, let's say, me, Anshul. Like, I want to find out what all orders were placed by me. So I need to go through all of these entries and then return to the user. Now, fortunately for us, the system capacities are quite good. Like in SQL and NoSQL, the system capacities are good enough to handle such big traffic. But let's say we want to improvise the user experience. I am a very frustrated user. I am very impatient user, and I don't want to wait for 1 second or even a few hundred milliseconds. Okay, I want very quick results. So what the product might try to do is, it will try to shard this database into, let's say, 1000 shards, just for the calculation easiness. So each of these shards, 1000 shards, will now have 10 to the power 9, which is 1 billion entries. So all of these will have 1 billion entries each. And now let's say if this database was sharded along the user ID, okay, which means that our shard key was user ID, and hence one shard, like for example, let's say my data was in shard 1, then I know for sure that my data is not going to be in shard 2, shard 3 and shard 1000. Okay, like so on till shard 1000. So my lookup service, when I'm trying to fetch the data that, hey, give me all the orders placed by Anshul in last 1 year. Okay, we are adding a condition as well. So it knows that the data is placed only in shard 1. It doesn't need to go through 10 to the power 12 entries and find out. It can easily just ask shard 1, and on reduced database, it is able to handle my request. Now in optimized systems, 10 to the power 12, 10 to the power 9, I mean, it would be a difference of a few hundred milliseconds. But in systems which are so huge like YouTube, Amazon and so on, these are the experiences that people count for. Like, these are the experiences which makes this tech giants a tech giant. You know, now there is a possibility that, okay, some admin on the engineering side of YouTube or Amazon and all of these tech giants, they want all the order details. Okay, so instead of going through one database and trying to find out 1 trillion entries, it can send requests to these individual shards and tell each of them to return the particular entries. Okay, it can be, for example, the entry can be as simple as, give me all the orders placed by any user in last 2 weeks. Okay, because they want to do some analysis on top of it. They want to try and stop fraud. There can be a number of use cases for which this type of query might be very useful. So now, instead of going through a very big table, we can go to each of the individual tables and try to fetch those relevant entries and return to the admin. Now, all of these requests will be concurrent. First of all, like, we are trying to hit all of these shards at the same time, and all the 1000 requests to the individual shards would be like, hey, return me all the orders placed in last 2 weeks. So now each of the shard has a responsibility to go through the billion entries and fulfill the request. Compared to it, if there was a single shard, if there was a single server, it would take quite a significant time. Now, once all the requests are answered by the respective shards, this results will be combined and then sent to the engineer or sent to the admin for further analysis. Now, I know, okay, when I am saying that all the requests will be concurrent and we will try to parallelize and all of those things, it's not as simple as it appears. Okay, there is some overhead because we are trying to send 1000 requests. There will be some network overhead. There will be some other overheads which will try to increase the latency, but it's a trade-off. Okay, we are trying to reduce the size of our database. Along with it, there is some latency overload for the lookup server. There will be some network overload to try and combine all these entries as well. So we are aware, like we should be aware. All of us would not be aware about it. It's all right, but we should be aware of all of the things which are happening behind the scenes, that there are some benefits and there might be some trade-offs which we need to realize while we are designing all of these systems. So surely sharding helps you to improve the read response time, something which happened for a few seconds. Let's say, like if it was 1 trillion entries and I wanted to find out one row out of it, possibly if it is not a primary key, okay, let's say it's not a primary key, then it is going to take me some seconds, like it would be in the order of 1 second to 1 minute as well in some of the use cases if the indexing is not done properly. But now since we have sharded, we have multiple shards, multiple databases, along with we can parallelly try to find the response. So this reduces in the order of seconds to probably a few hundred milliseconds. So this is a big plus, though it would be like, hey, for a few milliseconds it doesn't matter. But I have seen, like I have talked to some of my friends, they try to optimize, like they were trying to optimize from 400 millisecond to 300 millisecond. Okay, and reducing it just by 25%. Okay, now 400 to 300 is 25%. Just by reducing the latency by 25%, it helped them like get billions of profit, like billions of dollars of profit. It might seem crazy, but that's what the things are going on in real, like tech giants, real systems. Now, one more important advantage of sharding is improved write times or write throughput. Now, I was having this discussion with my flatmate, okay, and I was like, let's say there is a single server, okay, and there are a few hundred entries to it. Now, usually when concurrent write requests are occurring, there are two options. Either we serialize it or we don't serialize it. Now, for example, let's say it's a bank transaction where we don't want double deductions to happen, or let's say, you know, double charges to happen. We want to be very sure about the consistency of our system. For example, let's say I'm trying to do some payment through my UPI and I'm also trying to do some payment through net banking. Now, if both of them try to access the same database, it can happen that I was having 100 rupees in my balance and I tried to deduct, like I try to make a payment of 20 rupees each. And since both of them are occurring at the same time, there is a possibility that both of them read the same number, 100. Both of them try to deduct 20 rupees from it, which makes the balance 80 rupees, and then this 80 is written over 100. But even though we made two transactions, the real balance should have been 60 rupees. So in some of these use cases, this consistency is really important, and hence we would not be there would be serialized writes, which means that you cannot do two writes at the same time. So we will try to cover the use cases for both of them when the writes, concurrent write can happen on different rows. On the same row, it's not possible at all. We don't want to do concurrent writes. But on different rows, we may or may not allow depending on what the system actually is. Okay, now let me get rid of this example. Let's first talk about serialized writes, wherein we don't allow more than one write in the entire database. Okay, now this makes an obvious sense that since all the write requests, like that's, let's say this is write 1 request, once it is done, we will send write 2 request and so on. Okay, now instead of having one server, if we divided our database into multiple shards and we had like 4 servers now, 4 shards, instead of one request, in the best case scenario, we could handle 4 write requests in parallel. Now, this is the use case when the writes are serialized, which means we don't allow more than one write to happen at one time. So now write 1 can happen in shard 1, write 2 can happen in shard 2, and this is for shard 3 and shard 4 and so on. In best case scenario, like based on the number of shards, we can try to parallelize the number of writes happening. Now, let's say like my friend was arguing that, hey, what if the writes are not serialized? What if we are able to, like there are 100 rows in this. Now our server is trying to make writes to each of these individual rows. Like at the same time, we can make all of these writes together, like write 1 till write 100. All of them can happen at the same time because they are not serialized. So now we need to realize one thing. Okay, there is one server which has a particular write bandwidth. Okay, if we realize what all different constraints are there, there are buses to carry these payloads. Okay, these are not the buses which go on road. There are network buses which carry the payloads for the write request. Now, as the number of write requests increases, let's say even if we have 1 billion data entries in this database, okay, we can parallelize all of them, but the bottleneck becomes our write bandwidth, the write network bandwidth. And in order to improve them, we obviously cannot cater all the 1 billion write requests at the same time, even though they are not impacting the other rows. Theoretically, we could send the parallel request to 1 billion entries, but practically the bottleneck is the write network bandwidth. So now if we try to shard our database into, let's say, 100 shards or thousands of shards and so on, which is the real capacity of how much sharding happens in this big systems, you know, let's say even if it's like we had 100 rows, we divided into 10 shards of 10 rows each. Now, because of the constraint, because of the bottleneck of network bandwidth, we multiply our write network bandwidth by sharding. And this means that even though theoretically our initial system, our single database system was able to handle concurrent request, write request to all the rows at the same time, it was not able to respond to it because of the bottleneck in our write network bandwidth. But now, since that bandwidth has been multiplied, if the writes are corresponding to those individual different shards, 10 different shards, okay, write bandwidth has multiplied, and now because that bottleneck has eased down, what we were talking about, which was possible theoretically, we were saying that 100 writes can happen at the same time, which was not possible practically. Now that theoretical thing can be replicated in the practical use case as well. So this obviously happens us with better write throughput as well. Now we need to understand this is beneficial for use cases where the writes are happening in different shards. We need to shard the systems in a particular way. Now let's say, for example, if the writes were happening in one shard only, so even though we have multiplied the write network bandwidth, it's not going to give us the results, because now again all the write requests are going to the same shard. Okay, so we need to be very mindful how we are sharding our database, what logic we are using, what approach it is, okay, which we are going to talk very soon. And obviously, like, what is our shard key, what are the ranges and so on. So we talked about 4 advantages, starting with scalability, which was an obvious one. Then we talked about high availability, which is very important. And then we talked about better read response time and better write throughput. Now, I told you earlier, you know, all the glitters is not gold. There are a lot of disadvantages as well. And let's try to cover all of them one by one. Okay. Now, before I explain what data rebalancing is, I want to explain a situation that can happen very commonly in sharding if we are not very cautious about how we have sharded our database. So if you remember the earlier example, when we sharded the user table, we had a alphabet range. So let's say now if I have an alphabet range of A to H and then I to, for example, M, N to U, and then V to Z. Okay, now these are 4 ranges in which we have sharded our database. Okay, earlier it was A to H and I to Z, but now I have just changed the ranges for each of the shards. Now, if you are aware, like Indian names usually like R, S, T, like those are the very common alphabets with which Indian names start. Obviously A, K and all of those are there. But my estimation, and I have not studied it, but let's assume hypothetically that majority of the names lie in the 3rd shard. Okay, and this can be 60%, 50%, I don't know. Hypothetically, let's assume it's 60%. A to H contains other 20%. And I to M probably other 15%, and V to Z, it's a rare name. We won't have a lot of names starting with X, Y, Z and so on. So how much is remaining? This is 80, 95 and 5% is remaining. Okay, now let's assume the previous situation where we were sending concurrent read request and write request and so on. Now, even though we have sharded the data in our shards is quite skewed. Okay, ideally we would want 25% each, but that is obviously not the correct expectation to set. It would be like all of them should somewhere be between 20 to 25%, like 20 to 30%, so that we can achieve the scalability and concurrency that we were expecting. Now, if there is highly skewed data in one shard, then the ultimate motivation of scaling our database fails, because most of the read and write requests again are going to the shard 3 only. Okay, let me just write the shard names. So most of the requests are again going to shard 3, which defies our purpose. Now in this situation, what we do data rebalancing. Okay, this is where data rebalancing comes into place. Now we can either just reshard the shard 3. Okay, we just try to, like, n to u, we can just try to increase more ranges, like it can be n to p, for example, then q to r, and s to t, and so on. I mean, I don't know, I'm just giving a hypothetical example. But one such approach can be like this. But usually when we reshard it, it's highly possible that we try to increase the ranges in other shards as well, which would mean that the data that is currently lying in the respective shards won't live at the same shard, like they would need to be replaced to some other shards. And when this migration happens, there will be some downtime. I mean, let's say shard 1 changes from A to H to something like A to K, for example. So earlier the data which was there in shard 2 needs to be moved to shard 1, and probably like all the shards will be reorganized in some way. Or let's say we changed our partition key, our shard key, from name. Okay, earlier it was name, if you remember. Now it becomes user ID. Okay, now this changes everything altogether, right? So there is no correlation between username and user ID, and it is possible that none of the data which was lying in the previous shards would be in the same shard again. Now this incurs downtime, and it obviously affects the availability of the system, right? So this is a big cost if we are not sharding the database by proper partition key, proper shard key, or proper approach. Okay, like this was a range based sharding. If we, like, this is not a very good way to shard the database, because we decided these ranges. Okay, these ranges which were decided earlier was based on what the distribution of the current data is. When your system grows, this distribution might change. We are not aware what new users will be added to our database. So it is highly possible that current situation will differ highly with the future situation, and these rebalancing will keep on happening at regular intervals. So downtime will also keep on occurring at regular intervals because of the migration, and this is one of the disadvantages in case the shards grow disproportionately. Now this affects availability. Okay, availability is affected. Now let's talk about the second disadvantage, which is costly join operations. Now, if you have taken your database classes in college, or if you have read some articles, you would know what joins are. If not, I am going to explain in brief what joins are and what databases, like why do joins are required, why are joins required. So let's say there are two tables in a database. Okay, a database can have multiple tables. So this is T1 table and this is T2 table. Now let's say there are two columns A and B in this, and in T2 there are again two columns A and C. Now in this case A is the primary key. Okay, in T1 A is primary key, and in T2 A is foreign key. Now when we want to perform a join, okay, let's say this is for example, this is user table and this is product table. Okay, and A is a user key in this case, and C might be a product key or something like that. So now we want to do some sort of a join to identify what addresses, like B can be address, let's assume B is an address. Now we want to find some correlation between the products, which is C, column C, and what addresses they are delivered to, which can be column B. So in this case, we will try to do a join. We will try to identify from table T1 and T2 for the same value of A, what products were delivered to what addresses. Okay, this is one such use case in which joins can happen. Now imagine a situation in which this database was sharded. Okay, now this can be considered shard 1. Okay, now a similar shard 2 will also exist. Okay, Now the same tables are there, the schema won't change. Same tables are again there in another shard T2. Okay, now it is possible that we sharded our databases based on the user key, user ID, or it can be product ID. I'm not sure. Any one of the following, it is possible that let's say our user ID 1 is in table 1, but there are a few products which are also there in shard 1. Okay, now this is shard 2. I know I have messed up the left and right. Shard 2 is on the left and shard 1 is on the right. But let's say our user 1 in table 1, which is the user table, it lies in shard 2, but there are a few products ordered by user 1 in shard 1 as well. Okay, so there might be some entries corresponding to user 1 in another shard. Okay, so in this case, if you want to perform a join, what shard 2 needs to do is it needs to fetch the data from shard 1 that, hey, give me all the entries of user 1 in table 2, and then I will combine them, and so on for all the user IDs. And the same thing shard 1 also needs to do. Let's say in shard 1 table 1 there is a user with user ID 74. Okay, just a random number. So there is possibility that there are some orders placed by user 74 in shard 2 table 2. Okay, so in this case, shard 1 also needs to fetch some data from shard 2. It will also ask the entries from table 2 that, hey, give me all the entries corresponding to user ID 74. It needs to combine all the entries, and then like shard 1 will do its computation, shard 2 will do its join, and so on. Now this is only for 2 shards. Imagine if there are 100 shards. One shard will query from 99 other shards, and all of these 100 shards will query from other 99 shards. So imagine 100 shards querying from other 99 shards. There are 9900 queries of different user IDs from each of the other shards. Now this consumes a lot of our network bandwidth, okay, because these shards are not lying in the same machine, right? They need to be fetched from other machines, so it occupies our network bandwidth, and ultimately what would happen inside one machine happens across different machines and incurs latency. Okay, there is a cost of the read response time in this case, which reduces our latency. So costly join operations is, you can say, one of the disadvantages of sharding. So if we are not careful how we are organizing our data, we can incur higher latencies for some of our use cases. So in this case, the latency takes a dive in some use cases, obviously. Right? Now moving on to the third disadvantage. What if the schema changes? Okay, now until now we are talking about that, like in the different shards the schema will remain the same. You know, in the previous example also, costly join operations, we talked that table 1, table 2, user ID, address, user ID, and product ID, the schema is same across all the shards. But now let's say the schema changes, and to take an example, like if you remember in the dating application system design video, I talked about Tinder and Bumble and how they store their data. Okay, so we can assume that the data is stored, like username is there. Okay, let's just keep it name is there, name, then bio can be added, and photos can be added for, like I am uploading some photos, someone else is uploading other photos, and so on. So when my product is small, it is possible that I decide to keep the photos in the same table as my other user entries. Okay, now this is the user table. But once it has become a full-blown product where there are like millions of customers who are using the product, it is possible that storing the photos along with the other user information is not feasible from a technical point of view. So if you remember, like if you not watched the video, make sure you watch that video after you finish watching this video. But it is possible that we might decide to store photos in some other table. Okay, and that this can be a photo table, where we store the photos in the form of blob or some other choice. Like we talked about a lot of other options to store the photos. So this can be photo ID, this can be the bytes of the photo, and instead of photo over here, we change this to photo ID. Like there is a reference in the user table to the photo table. So since the schema has changed now, right, The requests which were coming to the earlier tables are no longer valid because we need to migrate the databases, we need to migrate the tables, and earlier, which used to be our sharding approach, might change after we have changed the schema. So this again can incur some downtime because we are changing the schema. Now, schema changes are not very frequent. Okay, these are big changes which may or may not be backward compatible. So schema changes should be avoided as much as possible, but at the cost of improving the performance, sometimes schema changes are really important. But on the other hand, it can cause side effects to a sharding approach, which might require to reshard our database. Okay, so while reshard, again the same issue which we, if you remember the first example, data rebalancing, we had to migrate the old data to new shards. So the same issue can happen with schema changes as well. So this can also affect the availability of our system. And this can be caused due to downtimes by migration. Okay, so now, until now, whatever changes are occurring as side effects of sharding, we saw a hit on our availability. In the previous example, we saw a hit on our latency. In the first example also, there was a hit on availability itself. Now, these are some changes which are visible to the user. If your system is not available, they won't be able to access it. The user knows about it, you also know about it. If the latency has increased, you know that your system is not optimized for some of the operations. The user also realizes those issues. Now, there is a very silent side effect which you might also not be aware. The user is also not aware, and at crucial times in crucial operations, you will realize that whatever you were expecting is not happening. And this can be potentially damaging. It can be a life and death as well in some use cases. Don't worry, I'm not exaggerating. I will tell you in what situations it can be life and death as well. Okay. Referential integrity is compromised. This is one side effect, possible side effect of sharding. Now, before I talk about what this disadvantage is, I want to highlight about what referential integrity is. Okay. Now, if you remember the previous example of user table and product table, I will just quickly redo it. So there is table A with columns A and B, and there is table T1 and T2, and this is column A and C. Now, A, if you remember, it was a primary key. Okay, this is a user ID, and in products table, we are using this as a foreign key. Now, for example, let's say a user wanted to deactivate their account from some service, okay, Flipkart, Amazon, anything. So if they deactivate it, their entry from table 1 will go because it's the user table, okay. Let's say the user ID was 30, okay. Now, this is removed because they wanted to deactivate it, all right. It is possible that there are some orphaned entries in table 2, which is the product table, right? Now, why I'm calling them orphaned? It's because there is no parent existing for this particular entry in the orders table. In table T2, it says that there are some entries corresponding to user ID 30. But if you check the main table where the primary key actually lies, the entry corresponding to 30 is not there. Okay, so it can cause to some misinformation when you try to fetch. For example, if you want to do some analysis, as I told earlier, okay, we want to do some join and try to identify which products are delivered to which places, and we want to do some magic on top of it by big data clustering and all of that. It is possible that whatever conclusions we are getting might not be right because they are influenced by data which should not be there. Now you would be like, this is so simple. I mean, if 30 is deleted from table 1, let's also delete it in table 2. This might sound simple if it was a single server. Now, if there are thousands of servers sharded across multiple machines, it is not so trivial. Okay. Why it's not trivial? It's because in sharded servers, most of the sharded servers and most of the SQL databases which are sharded across a cluster, referential integrity is not given. Okay, referential integrity is not guaranteed. In a single server, it can be guaranteed. Most of the SQL databases do provide that. But if the data is across shared databases, referential integrity is not guaranteed. Now, in this case, what we need to do, we need to write some code in our application server. We need to write some code on our own to try and delete all the entries from the other shards. Okay. First of all, let me make a note over here. In sharded servers, referential integrity may not be guaranteed. Referential integrity not guaranteed. Now, this leads to some changes in the application server, and this increases the operational complexity. This also increases maintenance cost because now we are responsible for that code. Earlier, SQL would be like, don't worry about it, I am maintaining the referential integrity, nothing will happen. But now the responsibility is on our hand, it's delegated to the application server, and they need to be very cautious that such changes are made as quickly as possible and they are consistent. So since I told that sharded databases don't have the luxury of referential integrity across the shared databases, this referential integrity is compromised and hence it affects the consistency. Now, in one of the real life case studies which I'm going to talk about, I'm going to tell how a hit on consistency affects the user experience. Okay, so in this case, you are not aware, right? There is no visible difference, like user doesn't know that, okay, there are some products in the product table corresponding to user ID 30. We don't know, like the engineers also don't know that such an inconsistency exists. So you might lead to some inconsistent data, inaccurate data in your analysis. So consistency is affected in this case. Now this is a silent thing, and this will not notify you. Even if you are monitoring, you might need to set up some cron job to try and identify if referential integrity is maintained over a period of time or not. So there are operational costs. Okay, let me write down what are the side effects of it as well. There is operational complexity. Okay, now there are maintenance costs as well because we are responsible for it and SQL is not. So these are the 4 disadvantages or 4 side effects of sharding which I wanted to highlight, because all the glitters is not gold. You decide that, okay, scalability is there, it's amazing, availability is there, it's amazing. But we need to be wary of what all potential side effects it can lead to. Okay, now a lot of talk about the advantages and disadvantages. Now it's time to talk about what all different types of sharding approaches are there. Okay. Now the first approach is horizontal or range-based sharding, which we have already talked about. But let me just talk about it once more in the context of what use cases it's more beneficial for and what disadvantages it can lead to. Okay. Now let's say our database, again, it was like there are 2 shards, shard 1 and shard 2. All right. Now this stores the data from A to H, and this stores the data from I to Z. Now, like we talked about the side effect of data rebalancing, which can happen, right? This is a side effect which we want to avoid as much as possible. And why this can happen is because like we are making a decision based on the current situation. Our current situation motivates our ranges, and our future scenario might not adhere to the previous ranges. So it is important to understand that we might need to rebalance it again and again, and there are incurred cost of availability. Our availability might take a hit. So now why use this? First of all, it's a very simple approach. I mean, there is no operational complexity. The application server side code is also quite straightforward. Like I shared in the example that, okay, there is some request for Rohan or Christina. We know that the lookup server doesn't need to do a lot of operations. Now, it is possible that there is some static data, okay, which doesn't change a lot in future. Let's say it's student data. Admissions are over, we have added all the students to our database, and now we don't foresee a lot of changes unless someone drops out, okay, which is also rare. But let's say we don't foresee a lot of changes in the future. Some changes might happen in the next year when a new batch comes in. So the data is not going to change, okay. It can have a lot of read request, right? Fairly possible. But in this case, our distribution, we are ensuring by some margin, we are ensuring that the distribution of the data across different shards might not change. So in the use case where there is static data, we might not need to worry about this skewedness. And obviously simple logic, very fairly straightforward, and less operational cost. I would not say no operational cost, but there is less operational cost. Okay, now we have talked about horizontal or range-based sharding. Now you might be wondering why we are calling it horizontal. I mean, is it because it's a kind of horizontal scaling approach? No, it's not. Now, up until now, we kept talking that the database schema will remain the same. Okay, we won't change it. But if you remember the example of Tinder and Bumble that I took earlier, where there is possibility of schema changes, it is possible that we might need to move to a different sharding approach. And for some use case, I am going to tell that in detail, but for such use cases, it is possible that we move on to an approach which is known as vertical sharding. Now, vertical sharding is not at all relevant to vertical scaling. Okay, this is not relevant to vertical scaling. Now, what vertical scaling would mean, we would try to increase the capacity of our single server itself. We try to increase RAM, we try to add more CPUs, GPUs, we try to increase the disk capacity, we try to add some buses for increased network bandwidth as well. We are not talking about vertical scaling over here. We are talking about horizontal scaling only, but the type of sharding is vertical. Now imagine, like I'm assuming a lot of you would be using LinkedIn and hopefully you are following me over there. But let's talk about the LinkedIn database, okay, what it would look like. There would be a user table. Okay, let me just change the color. Now there would be a user table which stores information about what company he or she is working in, what are the experiences, what is the education and so on. So there is user table. Now there can be a connections table which talks about that, hey, what all different connections Aanshul has or what all different connections you are having and so on. So there is another table for connections, or you can have it in the same table, like it depends on what type of database normalizing you are using. But let's assume that there is a different connections table, and then there is a different table for the articles that we are putting up. Okay, articles are the LinkedIn posts. Okay, let me rename it to post itself so that there is no confusion. So there is a post table as well. Okay, so now it is possible that if we are storing them all on the same server, it can bloat after some time, right? Like even though we have sharded it, let's assume it's sharded, it is possible that because of the size of the post, our current architecture of keeping all the tables together in one shard might backfire, because we are aware now people have started putting photos with the LinkedIn articles. Okay, LinkedIn posts, people are putting photos as well. There is some sort of an algorithm, I don't know what it is, but I have also started doing it. Now all the influencers are also doing it. So this can cause the database to bloat even though it is sharded. And we might decide that let's not keep the photos, like for the post table, okay, there will be some text, there will be some photos, there will be some likes, comments and so on. Okay, everything is there. Likes are there, comments are there. I'm not sure what other thing can be there. Reposts can be there. Okay. Now this is what I think is sufficient for a post table, but because of the photo column in this, it is possible that the post table bloats, and we might move to an architecture, as we discussed in Tinder and Bumble as well. We might move the photos table outside, okay, and we might decide to store it in a different shard. Okay, we might have a different shard for user table, shard 1 for user table. We are storing different tables in different shards now. Okay, and all of them will have different schemas. Let me mind you about that. Now connections table is in shard 2, and for post we are keeping two different tables but in the same shard. Like photos can be in a different photo table, and we can refer it using a photo ID inside the post table itself. So this can be shard 3, like post table is there, and then there can be a photo table as well. Now I am really sorry for my handwriting and drawing, but it is what it is. So Now this leads to a schema change. Obviously, we might need to incur some downtime as well because our features have changed. People have started behaving in a different way as what it was expected when the sharding was done earlier. So now our sharding approach has changed from horizontal sharding to vertical sharding, wherein we divide different features in different shards. Now, why this approach is beneficial? It's because our user table is a more confidential or a private sort of a table. So we might have different type of policies for it. For example, the consistency policy might be different. We might want to replicate the database or replicate the table. So our replication policies might also differ. And we might not want the same policies to be in the connections shard 2 or shard 3. Okay, so based on the type of feature, we now have the luxury of having different controls over all of these features. We don't want the user table to be compromised, so each shard has the luxury of choosing their own controls and own policies. This is one big advantage of vertical sharding. Now, a very crucial disadvantage which we might forget in the hindsight is that the features are still evolving. Okay, it is possible that we might need to reshard it. We might need to horizontally reshard it or vertically reshard it. We don't know. Features are growing, and it can lead to one feature getting divided into more such features and more such vertical shards in the future. So again, like this has the same disadvantage. We might want to reshard it, which can cause to migrations, like it can lead migrations, and this can affect our downtime and hit our availability. Right? So you need to be very cautious when you are resharding it. You need to think with forward compatibility in mind, that what features we are planning to roll out in future, how is it going to affect my current sharding approach, current sharding architecture, how will be my write and read requests be affected by it, and so on, and then make a call about what our shards should be and how they should be partitioned. Now the third sharding approach. Now these two were fairly simple, where we were dividing along the column axis or the row axis. Now the third type of sharding is a key-based sharding, okay, or a hash-based sharding. Now I will explain you like why we are using hash-based sharding over here. So let me give you an example. So earlier, if you remember, there was a table with a lot of user IDs, right? So let us focus on the user ID being the shard key over here. So the user ID can be 1, 2, 3, 4, 5, and so on. And let's say we want to have 3 shards. Okay, let me add a row 6 as well. And let's say we want to have 3 shards now. Okay, shard 1, shard 2, and shard 3. Now, if you remember, I told something earlier, which was like whenever the data is getting entered into one of the shards, we pass it through a function. Okay, it can be a hash function or it can be some other normal function as well. We do some computations on top of it. So it is some sort of a hash function itself. Okay, so we hash our shard key, and based on the result of it, like whatever the hash is in the response, based on the response of our hash function, we will decide which shard we should write the data into and which shard the data should be read from. So now let's assume a very normal hash function, which is in this case, like we can have a modulo 3 because there are 3 shards. Okay, and shard 3 will correspond to the modulo output 0. Okay, so now the first entry, user ID 1 modulo 3 is 1, so we will keep that entry in shard 1. Now shard 2 will have entry for user ID 2. Shard 3, for shard 3, the entries 3 and 6 will go in shard 3 because 3 modulo 3 and 6 modulo 3, both of them are 0, and so on. So 1 and 4 are in shard 1, 2 and 5 are in shard 2, and 3 and 6 are in shard 3. Now let's say there is a request that, hey, can you return me the response? Like I want the email ID for the user corresponding to shard 1. So now first of all, we will do the hashing. We want the output for user ID 1. So we will follow 1 modulo 3, which is our hash function. 1 is the shard key over here. Okay, and the output in this case is 1. So now this will decide which shard the data should be fetched from. So it will tell that, hey, my output is 1, so please get the data from shard 1 and so on. And similarly for the write also, let's say there is a new entry. So it will be user ID 7. So we will try to compute in order to compute the hash for it, we will try to compute 7 modulo 3, which is going to be 1. So we will put the entry corresponding to user ID 7 in shard 1. And if it further grows, we'll put the other entries as well. Now let's say our database has bloated. Okay, now there are 10 users and we want to reshard it. If you remember in data rebalancing, we want to do it. So it is possible during peak times, like for example, Diwali is coming, so Amazon and Flipkart, they would have a lot of sales. So that traffic will increase at such times. For example, Hotstar, okay, World Cup final is there or some other occasion is there. So at that time, the traffic will increase and we want to scale our database by increasing the number of shards. So right now we have 3 shards. It is possible when we are expecting a traffic spike, we might want to increase it from 3 shards to 5 shards. Now, what happens if we increase to 5 shards, right? We need to change the hash function as well. If the hash function was the same, shard 4 and shard 5 will remain empty because there is no output, like the output of the hash function which matches to those shards. So we will change our hash function from modulo 3 to modulo 5 now, and we might need to rearrange our data. So let me just get rid of the main table and we can see how it affects our data entries. Now shard 1, shard 2, shard 3, shard 4 and shard 5. So user ID 1 and 5 or 6, yeah, 6 in this case, 6 modulo 5 is 1. So 1 and 6 will be in shard 1, 2 and 7 in shard 2, 3 and 8 in shard 3 and so on. Now the current data is differently organized than what the ideal data should be for 5 shards. So now what this will lead to, this will lead to data rebalancing. We will need to update our shards. And in this approach, when we are increasing the number of shards or decreasing the number of shards, since it is difficult to change the hash function in between, we might need to stop the system from adding, like from having new writes or from having new reads. And again, this can affect our availability. So this can also lead us to downtimes when we are migrating from one hash function to another hash function. So it can lead to downtimes when we are migrating the data, and it can affect our availability. So now, like when the traffic increases, the traffic spikes, we might want to increase the number of shards. When it decreases, we might want to decrease the number of shards. And this elastic scaling will keep on occurring, scaling out and scaling in. Okay, scaling out means increase the number of shards, scaling in means decrease the number of shards. So these might be very frequent because a lot of sales are coming on and then they are also ending after a few days. Okay, Dussehra sale can be there, Diwali can be there, Black Friday is there, Christmas is there and so on. So it would be very impractical if we want to change the hash function and we want to incur downtimes again and again. So this is one disadvantage of hash-based sharding, and this you can overcome by using consistent hashing. Okay. Now this can be overcome using consistent hashing. I'm not going to cover consistent hashing in detail, but if you want to understand it in brief, I have talked about it in Uber's system design video earlier. So consistent hashing, we can use that to change the hash function on the flow. Now let's talk about the last type of sharding, which is directory based sharding. Okay, now this will help us to get rid of the side effect which was caused to us by hash based sharding, in which we were not able to change the number of shards, like elastic scaling was not possible on the fly. So first of all, if we are adding consistent hashing, it incurs some operational cost. Okay, it incurs some maintenance as well. So it is a costly operation, even though it helps to mitigate the issue of availability and downtime. All right. Okay, so now we are on the last type of sharding, which is directory based sharding, which helps us to mitigate the issue of elastic scaling. Okay. Now in directory based sharding, let's say we are following the same example as earlier. Let's say we have 3 shards, shard 1, shard 2 and shard 3, user 1, user 4, user 2, user 5, user 3 and user 6 in the respective shards. Now instead of computing from a hash function and deciding where the data should lie in or where the data should be fetched from, we will use a lookup table. Okay. Now the lookup table will tell you that for a shard key, what shard should the data be fetched from. Okay. So now if the shard key is 1, fetch the data from shard 1. Now it's kind of an index, you know. For example, there is a book, there is an index of what different chapters are there. So you can expect that what content would be in which chapter. So similarly here, the first thing that we'll do is we will have a lookup server with a lookup table, which will check in the table that where the data entry, like where the data should be fetched from, which shard should it lie in. Okay. Shard 2, shard 3, shard 1 and so on. Okay, like I'm assuming you will be able to understand which shard the remaining keys will lie in. So now, like we have understood what the flow is, but let's say there is a new data entry. We want to add a new user 7 to the table. So we will need to add an entry for that in our shard table or in the lookup table as well. So this is our lookup table. We will need a corresponding entry in the lookup table as well. So we'll need some sort of a function. It can be a hash function as well. So we'll need some sort of a function to decide which shard the data should lie in, but then that entry will be kept in our lookup table as well. So let's say we added 7 in S1 and so on, like our lookup table will also correspond to those changes. Now the key part over here is that how do we make into effect elastic scaling? Okay, we want to increase the number of shards from 3 to 5. So we change the hash function. How can we change it without affecting our availability? So the old lookup table remains as it is. Okay, whatever new entry comes in, okay, whatever new writes are there, they will correspond in a new lookup table and in new shards. For example, we are adding shard 4 and shard 5. Okay, let's say we are adding a user 11. So user 11, now we have a fairly new architecture, like we have a fairly new database, global database, ranging from S1 to S5 now. Now we add a new user 11. So 11 modulo 5, it should be in S1 and so on. Like we will keep populating. For 14, it will be in S4 and for 15, it will be in S5 and so on. New data goes into the new shards and we will keep populating the new lookup table. So if we want to fetch some data, we will first check into the new lookup table. If it is not there in the new lookup table, we will check in the old lookup table and fetch the data from the old shards. Now we need to migrate the old data to the new shards as well, right? So S1 from user 1 to user 10, we need to migrate them from the old shards to the new shards. So while this migration is happening, once we have migrated, let's say we migrate user 1 from the old shard 1 to the new shard 1. Okay, both of them, even though their names are same, they are different shards because they are different architectures. So when we move user 1 from shard 1, let me take a new example so that this confusion doesn't happen. Let's say 1 remains where it is. We move user 4. So it is no longer in shard 1. We move it to shard 4, which is a new architecture. So in the old lookup table, we will get rid of this entry corresponding to user 1. And in the new lookup table, we will add the entry for 4. That user 4 should lie in shard 4. Once all of these migration is over, we get rid of the old shards, we get rid of the old lookup table, and we now have a new lookup table with new architecture. In this way, same way, like if we want to scale it in as well, we want to reduce the number of shards, we can again change the hash function and use the same approach to like reshard it. This doesn't affect our availability, which used to happen in the earlier case because there was no bookkeeping possible for two different places. Okay, we don't know where the new data would lie, we don't know where the old data lies. So without a lookup table, this was difficult. But now again, all the glitters is not gold here as well. What's the issue? The issue is there is a lookup server which incurs some latency cost as well, because now we need to check in the table where the data should lie and then fetch it from there. Okay, so latency is taking a hit. And also we are taking one more hit, which is single point of failure. Now imagine what if our lookup server goes down. Lookup server goes down, you have no way to add new data to the database. We have no way to fetch the data from the shards as well. Okay, so our availability goes down in a way that it is a single point of failure. So obviously there are ways to mitigate it, single point of failure. Now for such crucial databases, for such crucial tables, we will have a master-slave architecture, wherein if the master goes down, we will make the slave a master, or if there are multiple slaves, then we can do some sort of an election to elect which slave should become the master. Okay, so now these are the different types of sharding. We talked about different advantages, we talked about different disadvantages as well. Now it's important to understand when we should actually use sharding. So now we need to understand that when we should actually use sharding, because we saw the good sides, we saw the bad sides, every coin has two sides. So when we should actually use sharding, we should use sharding when we know for sure that our single server architecture, our single database architecture is no longer able to cope up with the increasing traffic. Okay, so this is number one. When we know single database can't handle it. We also need to have an awareness of what all different features are there. We need to understand what our shard key is. Out of the 4 approaches I talked about, which approach might be best feasible for what shard key and for what use case. Okay, it is possible that we shard different features and different types and then fetch the data accordingly. So we need to be aware about that as well. Obviously, it will be adding some complexity. Adding some complexity, awareness of features, and so on. I mean, I have talked about when to use what type, what are the advantages of a particular type of sharding, what are the disadvantages, and so on. So by this time you would have a fairly good idea of what the optimal approach for sharding is and what my shard key should be. Now I promised you that we will talk about some real life case studies. So let's move on to that part. So the first case study that I want to talk about is Uber. Okay, if you have watched my earlier video on Uber system design, you would have a fairly good idea about how sharding is beneficial. For example, I am currently in Bangalore. Okay, now I want to find an Uber for me. Now I want to find the nearest cab drivers. Okay, I am at some location in Bangalore over here. I want to find some nearest cab drivers. Would it make sense for the server to check through the cab drivers who are currently in Los Angeles? No, right? I mean, that's just a waste of time. So in this case, we can shard the data in such a way that it's geographically distributed. These are known as like geo-hash based shards. Like geohashing is one way to distribute the data. So only the data which is near my current latitude and longitude, we only need to choose the nearest cab driver from that. Okay, there will be other choices like are they completing a ride, what's the end location, what's the start location, what's the driver history, and so on. But that's for some other time. I wanted to highlight over here how geo sharding is beneficial. So you must be aware that Uber keeps on adding new cities incrementally. Like when it would have started in India, it might have started with Delhi, Mumbai, Bangalore, and so on, all the cities, all the top cities, and then it would have moved to other cities like Ahmedabad, possibly Gurgaon, Pune, Hyderabad, and so on. I am not sure. But the point here is they are scaling rapidly. They are entering new cities. They are entering new territories. Okay, so it would make a lot more sense if we are storing that data based on the geography. The shards are based on the geography, and then we are fetching data from the same. It helps to improve the performance. It increases the user experience as well by reduced latencies. Okay, now this was one use case of Uber. Now talking about the second use case of Instagram, like it's fairly similar to what I talked about LinkedIn and Tinder case study earlier as well. Now when Instagram would have started, they obviously would have expectations that it would be at the stage where it is right now, but they would have started with a very simple architecture in the beginning, and when the number of users increased, they would have thought that let's shard our data by the connected graphs. What I mean by connected graphs, for example, there is Aanshul. I follow some people follow me. Okay, so it forms a sort of network. So it would make a lot more sense if we would shard the database based on the user IDs and the connections. So if I have a bunch of friends, like let's say I have 5 friends only on Instagram, okay, hypothetically. So we 5 friends interact with each other a lot. So it would make a lot more sense if my connected network was in the same shard. And similarly, there would be a lot of other connected networks as well. And those connected networks should ideally be in the same shard itself. So for example, if I'm commenting on my friend's photo, then he or she, they are lying in the same shard as mine. So consistency or the referential integrity which I was talking about, consistency doesn't take a big hit. Okay, so this becomes a good idea. Like we can use user ID as our shard key, and it also helps us with consistency because my connections are in the same shard and so on. So when Instagram grows, like I don't know, there might be 1 billion users using Instagram right now. It might increase to 2 billion users and so on. So now for this case study of Instagram, we saw how clusters, like sharding by clusters, is helpful based on our connections and user ID. So in case if the traffic goes, like increases from 1 billion to 2 billion as well, right, the same approach might be beneficial. Again, like they would not have to reshard it, they would not need to change their approach, and it helps to improve their performance and also consistency and all of those other factors. So latency is intact because we are sharding, like the data is distributed. Consistency is there and availability is also there. I mean, if one of the shard goes down, then it is possible because of the replicates. There will be master-slave architecture for such crucial databases that the slave server can come up and handle the traffic in case the master server goes down. Now the third case study is interesting. Right now I have talked about 2 case studies in which sharding has proved to be beneficial. Now the third case study is of Reddit, right, where people post thoughts and some people comment on those thoughts and so on. Now what happened in Reddit was they decided to shard the data based on user ID. Okay, similar to what Instagram did. Right? Shard key is user ID. But now, as a consequence of this, like different users are in different shards. So now when one user comments on a post of another user, now in Reddit, there is not such strong concept of followers or following and so on. Okay, you don't just interact with your own friends, you will comment on any XYZ person's posts or their content. So what this approach led to was some inconsistencies and frustration among the user. Let's say I am, okay, Aanshul, and there is another person, Raj, who has posted something. Now Aanshul comments something on Raj's post. Now, since it is possible that both the users are in different shards, the consistency is eventual consistency and it might not take into effect as we have expected. So you are expecting that your comment should show up to Raj at that same time, but it might not happen so. So consistency took a hit because of this approach, because they didn't realize the side effects of their approach, like shard key as user ID. They did not realize this side effect of consistency. Okay, so consistency took a hit and people were getting frustrated that I'm not able to see the comments, I'm not able to see the likes, the interaction is not getting propagated from one user to other user and so on. And this led to a decline in the number of users, and they had to rethink their strategy that, okay, it is improving the scalability. Scalability is a big plus, but I talked about referential integrity, like it can get compromised as well. It can lead to some data inconsistencies as well. So in the case of Reddit, whatever sharding approach they took, or whatever suggestion they went ahead with, it backfired with data inconsistencies and the number of users decreased, though at the cost of performance. But it is important to understand that performance doesn't just mean latency. Okay, performance doesn't just mean concurrent read responses and write throughput. It also means data consistency. So this is what got affected in Reddit by their choice.
Now let's begin with caching. I think we all have that deja vu kind of feeling, you know, when that techie friend of yours, suppose for example your application is not working, it's hanging a lot. So that techie friend of yours will come and tell you that, hey, did you try and delete your cache? Obviously, he has no idea what cache actually means, but that solution works for a lot of us. Now, let me try to explain what cache is in a more layman terms. Let's say your mother wants to cook something for the dinner and she identifies that, okay, there is butter in the refrigerator, there is cheese in the refrigerator as well, you have olive oil. Okay, now you guessed it right. Yes, I am making pasta. I have tomatoes with me as well, but I don't have pasta. Okay, so what will be your next step? Your next step will be to go to the grocery store and bring pasta, naturally, right? But now this is a costly operation. Let's say if you had pasta within your kitchen, in your refrigerator or storeroom, then it would be so much easier for you. This is exactly what caching is. If the information or the data is present in the cache itself, then we don't need to go and fetch it from the database. The disk IO is reduced tremendously, and okay, let me put it into different words. Let's say you go to the grocery store as well. Okay, you get pasta, along with it you will get other things also which you might require to prepare for tomorrow's breakfast, lunch or dinner and so on, right? In the same way, when something is not found in the cache, we go to the database, fetch it from the database and bring it to the cache itself so that it can be referenced in the future. So ideally, the concept of cache is like this. If you anticipate the usage of some data or some item from the database, you want to bring it to the cache, because the cost of going to the grocery store, aka the cost of taking things out from the database and writing to the database, it's naturally going to be much larger as compared to retrieving it from cache. So this is what cache basically means in layman terms. You want to store things inside cache for faster retrieval, for faster access when your application is running. Now, when I talk about cache, there are different types of cache. There is L1 cache, then there is L2 cache. Don't worry, I am going to throw some technical jargon at you, but with time you will be able to understand what I actually meant. Okay, so now let me fundamentally explain how caching works in a system. Okay, in a computer system, how does caching works? Let's say you get some request. Now it tries to fetch from the database. Now this is the DB. So when the request comes, it asks something from the database and the information which is requested is returned to the user, right? But now this is a costly operation. Now, if you want to find an analogy, you will realize that going to the grocery store is quite costly. You need to walk, you need to spend some time, you need to burn some calories as well, perhaps your fuel as well. So it's a very costly operation and we want to minimize on those costly operations as much as possible. So what we do is, instead of fetching it directly from the database, we will put in a caching system in between. Now this is a cache. Let's forget about L1 and L2 for right now. And no, it's not the visa thing I'm talking about, it's the cache. So let's forget about L1, L2 right now. And this is our database. So when the request comes, it comes through some sort of an application server. Okay, the application server is the server owned by your system itself, like you are hosting the website on some server. So that is the application server I'm talking about. So let's refer it as server itself. So when some request comes to the server, it first asks the cache that, hey, do you have this information or not? If the information is found, then the information is retrieved from the cache itself. This is known as cache hit. Okay. If the information is found, then it's known as cache hit, and then we don't need to go to the database and fetch that information from the database and return to the user. So in this way, we reduce the hop of fetching from the database and retrieving it to the user. Now let's say if the information was not present in the cache, okay, then it's known as a cache miss. Cache miss, if the information was not there. So now what will you do if there is a cache miss? Naturally, there are two ways. Either the cache or the server, either of them can ask the database that, hey, the information is not present in the cache, can you give me this information? So this information is then returned to the server directly. There are two ways. Either the information can be returned to the cache and the cache can return the information to the server. We will cover both of those approaches in detail further down the video. Or the database can directly return the information to the server itself, and then the server's responsibility is to store it in the cache because it was recently received. Now this is what we mean by cache hit and cache miss. Now let me explain it in more proper way that, for example, in the cache there is some information already present, 1 is already present, and in the database also 1, 2 and 3. These 3 pieces of data is already present. Now if the server wants to ask for 1, it will first ask the cache, and since the information is already present in the cache, 1 is already present, so we will return the result or the 1, the data 1 from the cache itself. Now let's say it asks for 2. Alright, the server requires 2. Now it will ask the cache will be like, I only have 1, I don't have 2 with me. So we will retrieve the information from the database, 2 is present in the database, and we will return it to the user. Meanwhile, we will also store the missing 2 in the cache, so that in future, if the request for 2 comes in again, we can return it from the cache itself instead of fetching it from the database. Now this is how cache normally works. I mean, if you look at the large system, it's much more complicated, and I'll explain what all different read strategies are there, what all different write strategies are there, and I will also explain some of the other concepts around it. Now you must be wondering, if cache is such an amazing thing, why can't we store all the information inside the cache? Okay, now here's a catch. Catch and cache, both of them are different things. So here's the catch. Now cache has costly hardware, and that is the reason it has a limited memory. Okay, for example, if you have a ROM of 528 GB, or we have all this 1 terabyte GB, 1 terabyte ROM. Now the RAM is 16 GB or 32 GB in usual cases, depending upon what laptop or what system you are using. But cache is much more smaller as compared to a RAM as well. So we cannot store all the information because of the cost issues. Now when I talked about L1 and L2, L1 is much faster as compared to L2, but much costlier as well, and that is the trade-off we need to manage, and that is the reason L1 is smaller in size as compared to L2, and so on. Like after L2 it comes the memory, and from the memory it goes to the database. So that is the hierarchy. From L1, L2, this is the memory, and this is the disk or database. Okay, now L1 is much faster and much more costlier as well, and that is the reason we have those storage issues in cache, and we cannot store everything in the cache itself. Now let me talk about some definitions related to the terms that you will hear in the in this video down the lane. Okay, one such thing is cache eviction. Don't worry, I'm going to explain this in detail, what all cache eviction policies are there, and the other thing is cache invalidation. Now imagine a situation, let me create a cache as well. Now let's say in the cache there is space for only 3 data objects, alright, and it is already filled with 1, 2 and 3. So now let's say if we have a request for 4, we will obviously in the cache 4 is not present, so we are going to bring it from the database. When we bring it from the database is like, I need to put in 4 in the cache itself, so that the request comes for 4 next time, we are going to fetch it from the cache itself. But since the cache is full, okay, since the cache is full, we need to get rid of one of these objects. 1, 2 or 3. 1, 2 or 3, we need to get rid of one of them in order to create some space to store 4 in it. Now this is known as cache eviction. This obviously happens, not usually, this obviously happens when the cache is full. Okay, and in order to get rid of some data point from the cache, there are different cache eviction policies which we are going to discuss in this video in detail. Now coming to the cache invalidation. Okay, let me create a database. This is a database, and I am storing a key value pair over here. 1 is corresponding to, let's say, my name Aanshul. Okay, Ansh, let's keep it there, and 2 is corresponding to Ram, for example. Now in the cache both 1 and 2 are present, 1, 2 and 3, all 3 of them are present. Okay, let's assume that 3 is also there in the database somewhere. Now this is the database. So now what will happen is, let's say there is a database update. Corresponding to 1, I change from Aanshul to perhaps Rohit. Okay, so the database will get updated, but in the cache there is an entry from 1 to Aanshul itself. Okay, so let me just get rid of Aanshul from the database, and I put in Rohit over here. Alright, Now corresponding to 1 in the cache, there is already Aanshul. I have not get rid of the Aanshul in the cache. Now this is when cache invalidation methods come into play, because something has got updated in the database and the information inside the cache is either stale or inconsistent. So this is also known as cache inconsistency. So we need to make sure that the cache at any moment is not inconsistent. Either we can get rid of this entire data entry altogether, like we can just remove one Aanshul altogether, or we need to update the entry from one Aanshul to one Rohit. Okay, so any of these tactics, these are the part of cache invalidation strategies or cache invalidation policy. So we are going to cover both of these in quite detail, but I just wanted to let you know what both of these actually mean. So now let us jump on to the next concept. Now before understanding the next concepts, let's first understand what are the advantages and disadvantages of using a caching mechanism. Now obviously some of the advantages are quite intuitive. For example, the first one being better performance. Now that was the reason why we introduced caching. Now the second one being lesser load on database. Now since we are fetching a lot of things from the cache itself, naturally the load on database will be lesser and the retrieval cost or any updating cost also reduces naturally. Now if you remember, I talked about cache miss and cache hit, right? So we would naturally want this ratio to be much higher. Okay, we want our cache hits to be much more than cache misses, and we want to prepare algorithms in such a way that it is as optimal and as higher as possible. Okay, if this is higher, then naturally the load on the database will be lesser. But if we create some cache eviction policies such that whenever we try to hit the cache, it always results in a cache miss, okay, then we are naturally going to get it from the database, and this is not going to reduce the load on the database. So we want such policies which help us to reduce the load on the database as well. And lastly, it helps to reduce the expenses. Now you would be like, you mentioned that cache is a costly hardware. So how is it reducing the expenses? So for example, let's assume you are facing some performance issues. You want to increase the number of cores. So you have two options with you. Either you can increase the memory or the number of cores in your system by purchasing some costly GPUs or CPUs or something like that, or you can have a mechanism of introducing cache in front of you. Now there is a trade-off between both of them, increasing the additional capacity by purchasing a new system or adding a caching mechanism. So there is a trade-off, but ideally it has been found that having a smaller memory cache which is faster in retrieval helps you to reduce expenses by a lot. Now let's understand what all are the disadvantages. Now you must be like, cache is such a great system, what all disadvantages can be there? Now if you remember, I already mentioned some of the disadvantages to you earlier, one of which is the eviction. Now when the cache gets full, we want to get rid of some data point from the cache and make space for the new data point which is fetched from the database. Now if the cache eviction policy is not designed properly, it can lead to a lot of inefficiencies, and the performance optimization that we are expecting due to cache, it might not happen. And that is the reason why we want to increase the number of cache hits against cache miss. Now the second disadvantage is data inconsistency, which also we discussed earlier, right? Now if something is updated in the database, we want the fresh information to be available in the cache, or we don't want that information to be available in cache at all. Okay, we cannot risk that. Okay, if you remember the previous example, we updated one Aanshul to one Rohit, right? So now if someone asks the cache that, hey, give me the value corresponding to 1, then the cache will return Aanshul itself, which is not the right information. So we need to avoid those data risks. Now this is a very trivial information. Someone might be storing their bank account number or some other sort of thing, which is very informative and privacy related. Okay, so we want the data inconsistency to not be there at all. We want the data to be as fresh as possible, and if not, the data should not be present in the cache. But we cannot risk data inconsistency. And last point is increased complexity. Now when I talk about increased complexity, I am talking about the complexity of the entire system design. If you are introducing one new component in your system design, it is going to lead to newer eviction policies, newer invalidation policies, and so on. So the coding part or the development part on the application developer or the cache developer also increases, along with the maintenance of cache itself. So it's a costly affair overall in terms of added complexity as well, but there is a trade-off related to the performance, and that is why we prefer having caching systems in almost every system, every large scale system you look around. So cache is going to be there, but we need to be aware about what all cache eviction policies we are using, how we are getting rid of the old data, and how we are trying to minimize the complexity in the system design as much as possible. Now I kept on talking about eviction policies again and again, so now it's time to understand what all different cache eviction policies are there. Let me note them down first, and then we'll go to each one of them in detail. The first one is LRU, and this is something which you must have heard a lot of times if you are a computer science student. Okay, just to expand it, it's the least recently used. The second one being MRU, and it's the opposite of the previous one, most recently used it is. And the third one being most frequently used. Now I will explain the difference between all of them, so don't worry about it. Yes, there are a few more. It's random replacement. I'll just put in random over here. And now if you are aware about stacks, then you would know there is something known as FIFO, first in first out. And then there is LIFO, last in first out. So now let's go and understand all of these eviction policies in detail. Now least recently used makes a lot of sense when we talk about, let me just prepare some cache as well so that this makes more sense. Okay, now this is our cache. There are 3 elements inside cache, 1, 2 and 3. Now when we want to make space for a new information inside cache, for least recently used or LRU, I will ask one question. Out of all the 3 elements, which one is the least recently used? So we will ideally have some timestamp associated with all of them, that okay, this is the timestamp when it was recently used, like whatever is the last access timestamp. Now out of 1, 2 and 3, whichever one was used the oldest, we will get rid of that particular element and make space for the new one. So if I want to give you an example in terms of a real life application, let's say for example the time when MS Dhoni retired, you know, he put in that post that at 1929 hours I retire from cricket, international cricket. Obviously we expect him to come in IPL next year as well, but at that time a lot of people were going to his profile on Instagram and trying to watch the video that he had posted. So what would happen is that naturally that post is going to be a lot more accessible as compared to other posts, and that post is going to be the part of cache in Instagram's profile or Instagram system. Okay, so now as that post gets older or staler, let's say he posted on 15th August, I don't remember to be very honest, but after 30 days or so that post will become like, that post will cool down and naturally it will get out of the cache system. Like it will make space for a new viral post which might be coming, or a new viral profile which is coming. So that is what least recently used means. We get rid of the element which was accessed the earliest, or which is the oldest present element inside the cache. Now most recently used is completely opposite, and you might be wondering that ideally we would want to get rid of the element which is older, which is staler. We want to keep the fresh elements inside the cache so that it is accessed quickly. Now let me give you an example. If you have not seen the system design video of Tinder which I prepared, make sure you check it out, because let's say you are on a dating application. Okay, you are swiping some people left and right. Now ideally what Tinder does is it stores those profiles in the cache which you are most likely to swipe, ideally swipe right, but yeah, that is how the caching system in any dating application works. Okay, now let's say you swiped a profile left or right. You don't want the same profile to come again, right? It would be a really bad user experience if I swiped someone left and the same profile is coming again and again. I'm like, I have swiped it left, I don't want it again. So naturally we are going to use most recently used eviction policy in that to get rid of that profile which we have recently used from the caching system. Okay, so in this case, I will just ask 1, 2 and 3 the same thing I asked earlier, that which one of you was most recently accessed, which one of you is the freshest one, and then get rid of it. Okay, now I hope LRU and MRU, both of them, make sense to you. Now the third one is most frequently used. Now we all use a lot of emojis in our mobile phone, right? So not exactly like MFU is not exactly used in emojis, but if you have noticed, it neither uses LRU or MRU. For example, if I get some emoji from the entire database corpus of the emojis, let's say I got some heart emoji, okay, which was not present in the recently used emojis tab that we have. So ideally we would want that emoji to be the part of the recently used ones, but it is not present at the top of that list. Okay, and that is the reason they use something known as most frequently used. For example, 1, 2 and 3. Now 1 might be the most recently used and 3 might be the least recently used one, but it might be 2 which is most frequently used, like people are using it more and more again and again, and that is how the ordering of the cache might happen for certain applications like emojis, wherein we want to put the most recently used one. Okay, my bad, I have explained something completely opposite over here. Now this needs to be least frequently used. We want to get rid of something which is least frequently used. Yep. So this is an eviction policy and not adding it to the cache policy. So in terms of eviction policy, we want to get rid of something which is least frequently used. So something which is used more and more often again, that is going to be the part of cache, irrespective of the fact if it was used 30 days ago or used just 1 hour ago. Okay. There can be something which was used 30 days ago, but it was used 100 times in a day, for example. Okay, that still might be present in the cache as compared to some element which was just used yesterday but just used once. Okay, so in certain situations, LRU might be more preferable. In certain situations, MRU might be more preferable, and in certain situation, LFU might be more preferable. It depends on the use case which eviction policy we want to use. Now the simplest one is going to be random replacement. We don't want to make our heads turn crazy. Whatever element is present, just point a finger at it, we are going to get rid of it. As simple as that. Okay, let me just draw the cache over here as well. So as simple as that is, we just randomly choose an element from the cache and get rid of it. Now first in, first out and last in, first out. If you are familiar with stacks and queues, you might be aware what these terms mean. Now irrespective of the number of times it was accessed, or irrespective of when it was accessed. Okay, for example, let me go back to the previous page. So let's say I accessed 1 30 days ago, I accessed 2 15 days ago, and I accessed 3 1 day ago. Okay, I'll just put in those days: 30 days, 15 days and 1 day ago. Now naturally in least recently used, I'm going to get rid of 1. In most recently used, I'm going to get rid of 3. Now what happens in, first out? First in, first out doesn't care when it was accessed. Okay, it is very much possible that the element 3 was added to the cache first because it was accessed on the 31st day, like 31 days before. 3 was added to the cache, and now recently when it was accessed again, the element was present in the cache itself. Since from the 31st day to the first day, the element was present in the cache itself. Okay, let me add some dates as well. It was accessed on 1st Jan and it was accessed on 31st Jan as well. So now when it was accessed on 1st Jan, we are going to add 3 to the cache. Okay, now it is still in the cache. We have not got out, like we have not got 3 out of the cache. On 31st Jan, it is accessed once again. Okay, so now it is the least recently used one if today's date is 1st Feb. But now when we go to FIFO, it will just ask one thing: when were the elements added to the cache, and get rid of the one which was added in the beginning. So now when we look at it, 1st Jan, 3 was added for the first time. 1 was not added, 2 was not added, none of them were added. Only 3 was added at that time, and it was the first one. So we will get rid of 3 in this particular use case. And for LIFO, it is completely opposite. Like whichever element was added to the cache, the last, it can be accessed, like it can be more recently used, it can be less recently used, we don't care about it. But the element which was added to the cache in the end, we are going to get rid of it. As simple as that. Okay, so these are 6 of the eviction policies, and depending on the use case, you need to choose one of them or probably create your own algorithm using multiple one of them. Now we discuss some of the eviction policies. It's time to move ahead and understand what all invalidation policies are there. First of all, I know it might be a lot of technical jargon, eviction, invalidation, inconsistency, and so on. So let us first understand what is what do I mean by invalidation over here and why do we need it. I know we have discussed it earlier, but it might be lost in the moment of this video. So let us first understand why is invalidation policy required. Okay, so here there is a database and there is a cache in front of it. Let's say one has lol in front of it, and in the cache also we have lol. Now for example, we can update the value for one from lol to roffle, or we can remove it altogether. Let's say we removed it. Okay, so now we don't want the cache to return some information which is not present in the database, or we don't want the cache to be in an inconsistent state as compared to the database. So ideally what we want is both of them are in sync with each other, right? If some data is present in the database, we want the same data to be present in the cache and not something else. If the database gets an update in the form of a deletion or an update as it is, like if the value is updated or if the value is removed altogether, we want to use some invalidation policies or write strategies so that the value in the cache is also updated. Okay, so now let's understand what all different invalidation policies are there. Let me get rid of all of these jargon and we'll move on to the policies. I hope you understood why we need invalidation policies and like in what situations we want to use those invalidation policies. If not, you can just add the comment below and I will be happy to answer them, but it would be self-intuitive by this time of the video. So the first one being write through cache. Don't worry about the jargons, I'm going to explain everything in detail. I'll just mention the name of all of them and go through them one by one. Okay, the second one being write around cache. Now I'm sure like with the language write through cache, you have some thoughts inside your mind and you might be right. I think you would be right, like understanding it from an English point of view, you would understand what it actually means. And the third one being write back cache. Now let's go to the first one and understand in detail what does it mean. Let me first create a rough diagram. This is the server which is going to send request for some data. Okay, now this is the database and in between is our little cache. Now what happens in write through cache is that if there is some sort of an update or write to the database itself, that request will go through the cache. If that information is present inside the cache, it will get updated, and then it's the responsibility of the cache that okay, hey database, this information is updated inside me, let me update the same information inside you as well. So for example, we had one lol. Okay, if it was updated to or okay or some sort of other particular value, then it will first be updated in the cache and then to the database. So first it will be updated in the cache and next it will get updated in the DB. So in this way we ensure that whatever information is present in the database, it is up to date because we are performing the write to the cache before the database. So we are guaranteeing one thing: if there is some sort of an update in the database, it is already consistent in the cache. Now there is one disadvantage of this strategy. We are performing writes at two places. Okay, we are first making a write to the cache and then we are making a write to the database. Now let's say I added these two values. Okay, for the sake of clarity, I just added lol in both of them. Now let's say lol was never accessed during the reads. Now the write that we performed in cache is completely useless if we are not going to access it in recent time. So it depends on the use case. If the recently written or recently updated information is not going to be accessed, we should ideally not use this particular strategy. We will talk about some different strategy which might be beneficial for that. But if our use case, if our access pattern is such that the recently written data is not going to be accessed in the recent time, then it is going to lead to higher write latencies. So this is something which is a disadvantage, higher write latencies. Okay, so this is a trade-off, like we have a disadvantage, but along with it we have something known as data consistency in our cache, which is a lot more important to us. So depending on the use case, we might choose this strategy to go ahead with. Now let's move on to the next one, write around cache, and I'll just draw the same diagram once again very quickly. Server, I won't use different colors this time, cache, and then there is a database. Now write around cache is like, as the name, like it's intuitive in the name itself that we are not going to write through the cache, we are going to write around it. So whenever a write comes, whenever there is an update request, okay, let's update the database. So we won't first make the amendments or make the changes in the cache. We will make the changes only to the database. We will bypass the cache altogether and just make the updates in the database. So let's say if lol was added to the database, it will just be present in the database and not in the cache at all. So this is the difference between write through and write around, and you can naturally see there is going to be a change in the write latency, because earlier we were writing at two places and now we are writing only in the database. So this is the difference. Earlier we were writing first to cache and then to the database, and now we are writing only to the database. Now this gets rid of the previous issue that we had. We had a higher write latency, and if the access pattern was such that the recently written information is not going to be read in a short duration of time, then it's leading to higher write latencies. So for those use case, this is a workaround. We can use the write around cache and try to get rid of that disadvantage. But now with this particular trade-off, we have another disadvantage in front of us. What if the recently written data is going to be accessed? Okay, what if the recently written data is going to be accessed by us in near future? This is going to lead to higher read latencies, because there are going to be a lot more cache misses. Okay, so let me just note that disadvantage down. Cache misses might increase. And now again, to just emphasize this depends on the access pattern. Okay, you would be like that, okay, in this situation, why not use write through cache? Okay, so these are two different access patterns in which one write strategy or one invalidation policy is better than the other one. So write around cache can lead to more cache misses if the read pattern is in such a way that we are going to read the recently written data. So if read is recently written data, then it leads to increasing cache misses, and naturally the read latency is going to increase. Now one more advantage of this particular strategy as compared to the write around cache is, let's consider a scenario wherein, now let's move to the last strategy, which is kind of best of both the worlds. I will let you know what I mean by best of both the worlds. Let me just recreate the same situation again. This is the server, this is our cache, and this is the database. Now what happens in write back cache is that we just write to the cache. Okay, if you noticed over here, we are just writing to the database in write around cache. In write through cache, we are first writing to the cache and then to the database. Now in this particular strategy, we are just going to perform writes to the cache. Now you might be wondering, if only the cache is updated, we need to update the database as well, right? So the solution to that is, the updates from cache to database are going to be asynchronous. Okay, the server's role will be over when the information is updated in the cache, and then it's the role of the cache to asynchronously update it to the database. Now you might be like, if we look at the disadvantages of the previous two approaches, the first approach had a disadvantage of higher write latencies because we are performing two write operations, and in situations where the read access pattern is such that we are not going to read the recently written data, it was useless for us. In the next approach, since we are writing in the database, we were causing a lot of cache misses if a read pattern was in such a way that we are going to access the recently written data. Now this is best of both the worlds. wherein the cache is consistent, it is not going to lead to any cache misses if the access pattern is in such a way that we are going to read the recently written data. Okay, along with it, it doesn't even cause higher write latency because we are just writing to the cache. So let me just note down the advantages of this approach. Write latency is less, and cache misses are also less because the information is present in the cache itself. We are not going to fetch it back from the database in case our read pattern is such that we are going to access the recently written data. So both of these are less. Now you might be wondering, if this is the best of both the worlds, why not just use this particular strategy? Now I will just pause for a couple of seconds and will ask you to think it through what all issues it may lead to. I hope you think through the issues that it might lead to. Let me highlight the issues if you have not been able to come up with them. So the first issue is, let's say there is a power failure, or let's say there is some natural calamity and the data centers break out. Okay, so the database is not updated, the information is only in the cache. So when the system reboots, the information from the cache is going to be gone because it's inside RAM. Okay, even if the cache is persistent, let's assume for a moment that cache is persistent. So if something goes wrong to the cache, if the cache gets corrupted or there is a power failure and cache server goes down, then we have not asynchronously returned the same information from cache to database. So in this case, the database is not consistent with the cache, and that is going to lead some issues if something wrong happens in between over here. Okay, if the write is going through and some sort of a thing happens like corruption of cache or power failure in cache, then the information which is present in cache is gone. So this is a very big disadvantage, and this must be considered in situations where the persistence of any information is important. For example, for Uber's use case, okay, let's consider that example. We have some payment information that for a driver, let's say he has taken 10 trips in a day, and that information is stored only in the cache, and there is going to be an asynchronous job after 12 hours or something like that, which is going to write it to the database. Some issue happened and the cache vanished. Let's assume hypothetically the cache vanished, and at the end of the day the driver opens his app or her app and looks at the number of trips he or she has taken, and it's going to show 0 just because it was not written to the database. Now this is going to be a lot more crucial in banking systems or defense related systems where the durability of the information is a lot vital. Durability is an issue which must be considered whenever we are thinking of an invalidation policy. Durability is less. So now these were 3 of the invalidation policies that we discussed, and based on whatever the use case is, or the read access pattern is there, or the write access pattern is there, if the write QPS is heavy, then the first approach might not work out well for us. If the read QPS is much heavy, then the second approach might not work out the best for us, leading to higher read latencies. The third approach if it requires higher durability, then you should not consider the third approach, but it performs decently well in terms of read latency and higher write latency. So now let's move on to the next part, where we talk about some of the read strategies, like how the information is passed from the database to cache if it is missing. Now let's make a note of all the read strategies first, like the previous time, and then we will consider, we will go in detail through all of these read strategies. The first one is cache aside. Now if you are reading some books, the name of cache aside might be something else, but at the core you need to understand what the read strategy is. It doesn't matter whatever name we are going to give to it. Over here I am just putting it as cache aside, and based on whatever book or YouTube video you are going to watch next, if you want to, then it might have some different name, but understand the concept at the core. Okay, the second one being read through, and the last one being refresh ahead. Now let's first cover the first one, which is cache aside. So what it means is, let me just recreate the infrastructure as well for the explanation. This is the server, this is the cache, and this is the database. Now let's say there is some information which the server wants to read. Now let's say the cache is also not containing that information. Let me just note some example down over here. We want to access 1. Okay, the server has a request for 1. It looks into the cache, the information is not present in the cache. So what it does is it fetches the information from the database, and it is the responsibility of the application server itself to write the same information down to the cache. So let's just look at what all different hops are there over here. Okay, my bad. The first hop is going to be a read from cache. Now, since it is not present over here, the second hop is going to be from the server to database, that hey, this information is not present in the cache, I want to fetch it from you. The database will return the same information to the server. This is the third hop, and ultimately the server is going to write the information to the cache. This is the fourth hop. Okay, so in this way, these are the 4 hops through which we are going to maintain the information inside cache. Now, ultimately, the missing information is going to be written in the cache. So this is a simple strategy, fair enough strategy. This might look good enough to us, but in the next read strategy, I'm going to explain what all disadvantages there might be for cache aside mechanism. Also, another important thing which we need to consider is that since the responsibility is on the application server to write the missing information down to the cache, there is going to be a lot more workload for the application developer, considering the cache eviction policies, data consistency, and all the invalidation policies. Those all responsibilities are now shifted to the application server. That is also one such disadvantage. Now let us consider what we mean through read through. Now this is our server, this is the cache, and once again this is our database. Now what happens in this particular use case is, let us just take the same example once again, like the database has the information 1 but the cache doesn't have it. So now when the server hits the cache that hey, I need 1 from you, the cache would be like, I don't contain it, let me fetch it for you from the database. So instead of the server hitting the database the last time, this won't happen. Okay, the hop from server to database is not going to happen. Instead, what we are going to do, the cache itself is going to ask the database that hey, I want 1 from you, server is asking from me. So the database will return the information 1, which is the third hop. Now this missing information is also present over here, and in the fourth hop the same information is propagated to the server. Now let me just remove this part because this is the part of cache aside mechanism. Now if you notice, you might realize that okay, this also has 4 hops, the previous one like cache aside also had 4 hops. So what is the reason why read through might be more beneficial in some cases than cache aside? So let us imagine a situation when there are concurrent requests on the cache that hey, I need 1. Like let's assume there are 3 requests on the cache that hey, I need 1 from you. Okay, all of them are asking for 1. Now in the previous use case, let us just recreate the same issue over there. All of them are asking for 1. For each one of them, the response from the cache is going to be I don't have 1. So what the server will do is that the server will make 3 different requests to the database, fetch that information, the same information. Okay, all the 3 requests are going to return 1 from the database, and the same 1 is going to be added to the cache. So there are 3 different hits to the database. Whereas in read through, what the cache will do is, hey, I have 3 requests for 1, let me do one thing, I will fetch it once from the database and return to all of these 3 requests. So in terms of those concurrent requests, only 1 request or 1 hit is made to the database. So the load for concurrent requests in cases of cache miss is going to be much less in read through strategy. Now you might be thinking that in the previous example, in the previous strategy, the server could have done the same thing as well, right? If it was sending 3 concurrent requests and it realized that the cache doesn't have 1 in it, it could have sent 1 request only to the database instead of sending 3 different ones. Now this is an example for a singular server. Okay, that is, over here we are assuming that there is only 1 server. What if there are multiple servers across the globe and all of these 3 requests are coming from different servers? Okay, now this request is coming from S1, this request is coming from S2 and this request is coming from S3. Now there is a global cache. I'm going to explain what global cache means as well so that you don't get confused. But all of these servers are different servers. They are going to hit the same request from the cache, and the cache will be like server 1, server 2, server 3. Don't worry, I am over here. I am going to fetch one for you from the database and return to all three of you. So in such use cases, read through is going to be much more beneficial as compared to cache aside. Now lastly, refresh ahead. Now one important thing to note over here is whatever information is going to be present in the cache, it is going to have some sort of a TTL associated with it. TTL is, my mistake, yeah, this is TTL. TTL is time to live. So there is some sort of an expiration period for each item present inside the cache. Okay, so there, if the access pattern is such that there is some hot data which is fetched on a constant basis from the cache, we don't want that data to expire. So there are two things when it comes to refresh ahead concept. One thing is refresh ahead factor. I will explain you what this factor means and how it influences this particular read strategy. So let's say the refresh ahead factor is 0.5. I'm just taking some example over here. And let's say the TTL is 60 seconds. For example. So if there is some piece of information which is accessed on 0th seconds and then accessed on 61st second and like so on, if the access pattern is in this particular way, then at the 60th second the data will get expired and it will get evicted from the cache. On the 61st second, which is just 1 second after the data was removed from the cache, it is going to be accessed back from the database and stored into the cache. Now we want to get rid of such a scenario wherein we know that okay, this is a hot data, this is going to be fetched on a frequent basis in the future as well. We want to keep it fresh. So what refresh ahead factor does is, okay, so let's just make a note of one more term, RAF. I will just put RAF as refresh ahead factor. Now RAF times TTL over here is 30 seconds. Okay, so what it does is, let's say the data was first accessed on 0th second. Let me just get rid of 61 over here so that you don't get confused. On the 0th second, information is added to the cache. Okay, added to cache. Now on 20th second, there is again a read for the same information. Nothing will happen. Okay, now consider the 30-second marker over here with, like, since 20 is less than 30, nothing is going to be, like, nothing is going to happen. No operation. And now on 40th second, if we access the same thing again, okay, we realize that this is a hot data, and since this is closer to expiration, okay, 30 seconds was RAF times TTL and 40 is greater than that, this means that it is closer to its expiry. So we need to refresh this data once again. We obviously don't fetch it again from the database because it would make no sense at all. But whatever expiration time that we had earlier, that is going to change now. Earlier it was 60 seconds. Now on the 40th second, if we refresh it again, the expiry is going to be updated to 100 seconds now. So it's going to be living much longer inside the cache if we understand that this is a hot data and it's going to be accessed more frequently. So this is how factors like TTL and refresh ahead factor influence the expiry of any data present inside the cache. So this is just an add-on read strategy. Like, this can be added to both the previous approaches. Like, we can add this in the read through as well. We can add this in cache aside as well. But I'm just explaining it as a standalone read strategy so that it makes sense. Like, what is the reason why we are having this particular way of updating the expiry time. So I hope it makes sense to you. And these were the 3 different read strategies that can be the part of your overall like code or whatever eviction policy or overall cache policy that you have. Now lastly, let me just cover, if you remember, I talked about global cache. Okay, so there are different types of caches which I want to cover now. The first one being, let me make a note of all of them first and then I'll explain it once again. Distributed cache. The second one being global cache that we talked about. And the third one being CDN. Now CDN is not exactly a different type of cache, The full form of CDN is Content Delivery Network. Now I will cover all of these 3 different types of cache in detail, so don't worry. Now let's get started with distributed cache first. Okay, I realized I just made a small mistake over here. So this is not Content Delivery Network, this is Content Distribution Network, my bad. I hope you understand the distribution over here. So what happens inside distributed cache? Let's say, let's go a step back and understand. Let's say we just have one system where the cache is present, and now since your user base is growing, you are getting more requests, you require more space for cache. Okay, you require more memory, you require more resources for cache, but ideally there is going to be some capacity for any system. So whenever you grow beyond that capacity, you are going to fork into a distributed network. So instead of one cache or one system where the cache is present, the cache is going to be distributed. It can be across the globe or it can be in the same room, distributed among different systems. Okay, so let me just create a larger cache. Let's say there are 1 million rows in it, and now it's not possible to add more information to the cache, but our user base is still growing. We still want more capacity for our cache. So what we'll do is, let's say we break this entire cache into 10 different nodes, and each of these nodes is going to be known as a cache itself. So instead of 10, just for the sake of the space which is present over here, let's say there are just 3 nodes. Okay, now all of these million rows of cache are going to be distributed across the 3 cache systems, the 3 caching servers. Let's call them cache servers. So the entire data, the global data, is going to be part of different nodes, and none of them is going to be intersecting with each other. Okay, if there is some row present over here, if let's say there is data 1 present over here, data 1 cannot be present in another cache server. So overall it's going to be very exclusive, and I'll just explain how the distribution will happen as well. So let me just get rid of the one over here, and let's say information 2 is present over here and information 3 is present in the 3rd cache server. Now it is also possible that instead of one application server, it's going to be a distributed network of multiple application servers. So over here also it can be server 1, server 2 and server 3, and these are app servers. Now one application server may not just hit one particular cache server, there is no association of that sort. It can hit any of the cache servers present across the globe. Now how to make a decision where to store the cache and how to retrieve from it? So there is something, now these are known as shards. Okay, whenever you distribute some data, it is distributed across shards. Let me just make a note of it over here. So now each of those servers are going to be having some sort of shard key. Based on that shard key, the data is going to be distributed across these cache servers. Let's say the shard key has an incremental way. Let's say the data is 1, 2, 3, 4, 5 and so on. Okay, 1, 2, 3, 4, 5, this is the shard key, and we just perform a modulo 3 over here since there are 3 cache servers. So ideally the first cache server is going to contain 1 and 4. The second cache server is going to contain 2 and 5. The third cache server is going to contain 3 and so on. Okay. Now we have some hash function which is going to distribute the data across the shards for the cache. Now whenever a request comes, let's say the application server, either of these application server. Okay. The request can come to either of these application servers. Let's say 2 wants to fetch 1. Now there is going to be some logic residing in the application server which is going to route the request to a particular cache shard. So now we know that the hash function is modulo 3 and the shard key for this is 1. So 1 modulo 3, it's 1, and naturally we would want to request that particular piece of data from the first cache server and so on. Now there might be a use case where we are going to upscale or downscale the number of shards in the cache. So right now we have 3. If we increase the number of servers for cache from 3 to 10, the hash function is going to change and the distribution of the data across cache is also going to change. So this is going to require some rebalancing. In order to mitigate this particular issue, there is something known as consistent hashing. If I go into consistent hashing, I think it's going to take 1 more hour. You can just Google it up, or you can just leave it in the comment section if you want me to create another video on consistent hashing as well. So there is something known as consistent hashing, which deals with the upscaling and downscaling of servers. Let's say the traffic increases, you are going to increase from 3 servers to 10 servers. Let's say the traffic decreases again, so you will drop down the 10 servers to 5 servers or 2 servers or even 1 server. So that will require some sort of rebalancing. So in this way, the distributed cache works. Now when we talk about global cache, this is self-explanatory, because like since we covered distributed cache, global cache is going to make much more sense to you now. There is just a single cache system, and these are different application servers. There can be a single database, there can be multiple databases, we don't care about it. The only thing we want to care is there is a global cache present at some place across the globe. So let's say there are multiple databases, there are multiple shards in which the database is distributed. Okay, we don't care about it at all. Let's say the application server asks for some information. This cache is responsible to store all of that information. Okay, we are not going to distribute the entire cache data across multiple servers. All the requests are going to hit this particular cache itself, and the data is going to be retrieved. If it is present in this particular cache, it's going to be retrieved from this cache itself to any of the application servers. Now, based upon the write strategies and the read strategies that we discussed, it can be the responsibility of the cache or of the application server to update the information inside the cache if there are any cache misses. Now, moving on to the last type of cache, which is CDN, Content Distribution Network. Now, if you have noticed, sometimes when the internet bandwidth is not too much, okay, the speed of the internet is not much, you try to load some website. So the website loads without all the fascinating fonts and everything. The styling is not there, but the content of the website loads. Some images load here and there, some are still loading. Okay, so why does this thing happen? Why is some information present or returned to the user and not the other information? So this is where CDN comes into play. What CDN does is that it stores all the static information. It can be HTML, it can be images. In some situation, it can be videos, but videos can be bulky, so more likely videos might not be there. But any static information is there, you can store it in the CDN, so that if there is lesser network bandwidth, we can retrieve some of the information from the CDN directly. So this is another type of cache which can be used. For example, if you check my Tinder system design video, so I mentioned how we can use CDN in order to return some photos with lower latency. Like you are swiping left and right, so it is performing at a very high speed. Okay, so we want the photos to be loaded with as minimum latency as possible, and for that use case we might be storing images of the more potential candidates for the matches inside the CDN. So that is a possibility. So just let me note down some of the information. So you can store some static data in the CDN. It can be HTML, it can be images, and that is the reason sometimes you see a website loading up and is unstyled completely and all the text is dumped onto the website itself. That is because it's returned from the CDN and it's waiting from the database to fetch the entire website. So these were the 3 different types of caching. And now lastly, we will move to the part where we discuss when not to use cache. Okay, you might be thinking that if cache is so useful, why should we not use cache? So let us understand some of the points when we should not be using cache. So the ultimate purpose of using cache was that we want to reduce the access time, and for that we are introducing cache in front of database so that the access from cache is faster than database. But if the access time is almost comparable, then we must not use cache, or we must change some sort of strategy, either the eviction policy or the data invalidation policies, the cache invalidation policies. Some policy must not be the right, and that is the reason it is causing longer access times. So we must at least either change them or not use cache at all. So if the access time from cache is equivalent or almost in the comparable ranges, ideally if the database fetch is taking 1 second, then we would expect the order for the access time from cache to be in the order of milliseconds. So if the order is almost similar, then we must not use cache because it's a costly hardware. Now, second reason or second situation when cache might not be that much beneficial, and that is when the access patterns are not repetitive. Okay, what cache eviction policies do is that they try to leverage some repetitiveness in the access of data. They have some memory access patterns which they try to exploit and leverage in order to put some information which you might use in future. Okay, and that was the pasta example, right? When we go to fetch something from the grocery store, we are going to bring some more items along with us because we anticipate the usage of those ingredients. So we anticipate the usage of some data. That is the reason we add it to the cache. But if there is higher randomness in the access patterns, let me note that down as well, higher randomness or lower repetition in the access pattern, then we must not use cache, or we must find an alternative to try and improvise it. Now the third point being, if there is a lot of write QPS which is going to lead to more frequent changes, then it will cause our cached version to be out of sync, and that will lead to more accesses from the primary database itself. So that is also not favorable to us if there is higher chances of the cache data to be out of sync. So if there are higher updates, then cache might not be as beneficial to us. So these are three reasons which I feel can influence your decision whether you want to use cache or not. And we have also discussed some of the read strategies which might be beneficial in some case or not. We also discussed about some invalidation policies which can be beneficial in some situation over the other, and some of the eviction policies which we took the example of Instagram, we took the example of Tinder as well, and then we took example of emojis as well. So in different use cases will demand for different policies, and there is no perfect solution. First of all, one shoe will never fit all. There is never going to be a perfect example or perfect solution for anything. So make sure, depending on the use case, you make the right choice for cache.
Delicious. Delicious was a website that offered users to save bookmarks so that they can access it from any computer. The website was started in 2003 by a college student and was later acquired by Yahoo in 2005. This was way back when Chrome was not there and there was no bookmarking service either. By the end of 2008, the website had more than 5 million users and approx 180 million bookmarks saved. This scaled from one laptop to 5 million users. We'll start from the day it went live on the creator's laptop. Let's start by understanding what happens when you type delicious in the browser. Now, browsers do not understand the names. They only understand IP addresses. Hence, we need a way to convert this URL into an IP address. In case of delicious, DNS will return the IP address of the computer on which it is hosted. Now, since every machine which is connected to internet gets an IP address, and every time we connect to internet, this IP address may change. Therefore, we need to associate a static IP which does not change when you connect to internet again and again. And we need to assign this IP to the computer. To get the whole system up and running, we first need to purchase a domain name called delicious and then map it to the static IP of this computer. If you look closely, there are two major kinds of requests involved. One is the get or the read request in form of get user bookmarks, and the second one is post or write request in form of add bookmarks. Using the IP address that is returned from the DNS, both this request will go to the same computer, and within the computer there will be two things running. One is the application server which will listen to all the requests that are coming to the HTTP port 80, and the second one will be the MySQL server which will store all the bookmarks that my users are trying to save. So till now my life is good. I'm running the website for free and I'm using campus internet. My database is set up on my personal computer, so I'm not paying anything for the resources, and I'm making money out of ads. Soon the website became an instant hit. The user base kept on growing and the challenges also kept on piling up in the same proportion. Every time a new bookmark was created meant that there is a need for extra storage to store this particular bookmark. Now, the best available hardware at that time was around 50 GB of hard disk, 128 MB of RAM. This was basically a Pentium 4 era. To keep up with the demand, he bought better hardware, meaning he bought a better laptop, a better computer. The bottom line is he bought more RAM or more hard disk or maybe multiple cores. But soon, even the best hardware available was not enough to keep up with the growing demand of the business. In fact, most companies of the era focused on upgrading their hardware to solve the growing needs of the business. This form of scaling is basically called as vertical scaling. However, Delicious founder was different. He knew in the longer run his approach will not work. Not only he will be restrained by his system resources, but he might also lose valuable customer data if his laptop crashes. This website is not reachable when his computer is turned off. Hence, this computer was a single point of failure. To overcome the challenges of vertical scaling, his friends suggested him to utilize their own laptops or computers. The idea was to uniformly distribute the incoming requests to available computers. This mode, where we are overcoming the scalability hurdles using multiple servers and computers, is basically called as horizontal scaling. Now, we know that the client talks to the DNS to get IP address corresponding to a particular website. But the question is, the website is now running on multiple server instances. We have, let's say, 4 servers running the Delicious website. Which of the 4 servers available should be stored in the DNS? If I randomly choose any of the available server, all the requests will go to that particular server and that server will eventually die. To fix this, have one machine whose responsibility is to route the traffic to the available instances. This machine will lie between the DNS wall and the servers that I have. And the DNS configuration in the registry, I'll mention the IP address of this special machine and not of any of the instances that I have. Now the question comes, won't this special machine also die if all the requests pass through it? The reason why this special machine will be able to handle higher traffic is because it is only routing the traffic that it is getting to one of the available instances. It is not doing any compute or memory intensive task. And modern day machines can handle up to 1 million requests per second. So using this, we have solved for high number of queries per second on my system. But there is one more problem that still exists. That is single point of failure. Just like any other computer, what if my special server also dies? To solve this, we can have a standby routing server which will not serve or route any request. When my main server goes down, swap the main server with the standby server. But how do I swap? Should I change the IP address in the DNS registry? Doing this will take minutes. Can we do better? Yes, we can. Remember, we assigned a static IP to the special server. The key here is take the static IP and assign it to the passive one. Passive one meaning the standby server. The special server we just spoke about is called load balancer, and we will study more about it in the upcoming videos. That was all for this video. Register for our free masterclass on system design to get insights on how to design a full-fledged system. Link is given in the description below. We will keep on adding videos on similar topics. Hence, please click on the bell icon and get notified about our new videos. If you want us to do a video on specific content, please leave the topic name in the comment section. Please like, comment, share and subscribe to our channel.
We generate around 80 zettabytes of data today, which is almost 40x increase in the last decade alone. The need for data scientists and machine learning engineers is skyrocketing. Experts estimate that this data will grow even more to 200 zettabytes by 2025. Have you ever wondered how this data is stored? Can this data fit into a single server? Most of the software engineers talks about partitioning the data to solve for the limitations that is posted by a single server. Hello and welcome to my new video on sharding. I'm Mohit Yadav, and in this video I'll try to explain you the basics of sharding, and also I'll give you some of the strategies that is associated with sharding. When it comes to managing large data sets, we really have 3 choices. The first choice is vertical scaling, or functional scaling, or horizontal scaling. The vertical scaling is increasing the capacity of server on which data is stored. If the capacity of the server was earlier, let's say 512 GB, as the storage needs increase, we might want to migrate it to a server that can hold up to 1 TB of data. As you might have already guessed, this is not a very scalable approach. Hence, let's look at the second approach, which is functional scaling. In functional scaling, we try to split the data logically. I'll give you an example. Let's say you are running an e-commerce website And initially there were not many users, so you were storing everything in a single data node. All the tables which are keeping information about the users, their purchase history, and inventory was also stored in a single database in a single node. Now, as users are increasing, as you're getting more users, their purchases will increase, the number of users will increase, the inventory will also increase if you are onboarding new sellers. So each of these tables will independently increase. One way to scale your application is to break it into smaller pieces. One application will manage the users, the other will manage purchases, the other will manage the inventory. You might also have different microservices managing each database and sharing the data to other services via API. This logical split is almost always implemented at the application layer, meaning that there will be a piece of code which will be responsible for routing the read and write request to the designated database or the designated microservices as well. This is what we call as functional scaling. Horizontal scaling is what is called as sharding. In simple words, sharding is a way to split and store a single logical database or dataset over multiple servers called data node. This is in contrast to functional scaling, where we were splitting the data logically. We are segregating users, orders, purchase history, inventory into different data sets or microservices. Here, I will be splitting a homogeneous set of data, homogeneous table. For example, I will be splitting a user table or an order table. This is what we call as the sharding, right? And because of this very reason, because it is a uniform way of splitting data, we split the data based on one column of a particular table. Because of this reason, it can be automated and it can be implemented at an application layer or at a database level as well. Now let's try and understand how database decides where one row will go or where it will not go, which data node a particular record needs to be stored. To understand that, let's see how a request propagates through the entire system. All the requests will start from what we call as a client. A client can be a mobile device, a web browser, or living room device as well, right? From the client, the request will go to the load balancer. I'm skipping the DNS resolution step. So it will go to the load balancer. Load balancer will then transfer this request to one of the many available application server, right? This was application server. This will again be an application server and an application server. The application server will then push this message. Let's say it's a write request. So it will try to write to a database. Currently, since we just have one data node, all the requests will go to this particular data node called data node 0. Now, as the volume increases, what we want to do, we want to split the data to two different data nodes, right? So let's add two more servers. So this is server 0, this becomes server 1, and this is server 2, right? Now, let's dig deeper into one table. Let's say we want to know about the order table. In order table, we are maintaining order ID, we are maintaining user ID, we are also maintaining the item ID. Let's say for simplicity, these are the only 3 columns, right? Now, for user ID 1 purchased item 1, user ID 1 purchased item 2, user ID 2 purchased item 1, user ID 3 also purchased item 2. Let's say these are the only 4 records. Now to split the data, what we need to do, earlier all the requests that were coming were going to one single data node that was available. But now, based on the value of any one of the column, we can decide algorithmically where every record is going to be stored. So let's try to insert each record, and the algorithm that we are following for simplicity's sake is the modulo algorithm, which is that I will take modulo of column value, whatever column we decide. Let's say I decide user ID and I take a modulo with the number of available server. How many number of available servers are there? 3. So modulo 3 will come. And this column that we have selected as a sharding key is user ID. Shard key is basically the column on which I'm determining how distribution of the keys will happen, right? So I'll take the first example. I take user ID. The first row will basically go to shard 1. So I enter order ID 1 here. The order ID 2, user ID is 1. Again, modulo 3 if I take, it is 1. So it will come here. The third one, the order ID 3, 2 modulo 3 is 2. So order ID 3 will come here. For 4, 3 modulo 3 is 0. So order number 4 will come here. That is how the distribution in an algorithmic fashion takes place. This can also be done in a slightly different manner, wherein we don't do things like this. We don't have an algorithm to determine where each row is going. But what we do is we create a namespace. We create one more table. We create one extra server here. This is called as a namespace server. What this does is it creates a mapping of every primary key. So for example, order ID 1 is stored in server ID 0. Order ID 2 is stored in server 1 and something like that. And whenever you want to retrieve this value, you first query the namespace server, find out which server ID is storing that particular record, and then query on that particular node. So there is one extra step that comes in this kind of a fashion.
So let's first look at why do we even need to learn CAP theorem. CAP theorem is one of the most basic principles of distributed storage. So if at all you think about building or working on distributed systems in the future, CAP theorem is a must-have, must-know. So that's why you need to learn CAP theorem. Now, before I get into explaining CAP theorem, and I would try to do that with using as simple example as possible, I want to give credit to Kaushik, whose blog I have borrowed a few ideas from. So thank you, Kaushik, for coming up with a very, very innovative example. So let's get to it, right? So to elaborate CAP theorem, I'll take example of a real world example of let's say you. Imagine I am an entrepreneur. I'm looking for ideas and I feel, you know what, like people need reminders. Let's build a service that just stores reminders, right? Which is, I get this very premium number. Imagine I name my company as ABCD and I get this very premium number, which is 1234, 1234. People could just call me on 1234, 1234, and they can tell me what they want to remember. And then when they call me back, I tell them what they wanted to remember, and then things work. It seems to me that this is a great idea. So what I do is I set up this line. I sit in the office. Imagine this is me. Forgive my drawing. Imagine I sit in the office. Every time somebody tells me, let's say I got a call from X, and X says, hey, please remember that I have a flight tomorrow at 9 p.m. I say, great. Next time they call and they ask me, tell me what I wanted you to remember. And then I tell them, you know what, you have a flight tomorrow at 9 p.m. And then this seems great. I charge people very nominal amount of money to store this information, and service takes off. Everybody needs this. There's a big market. Everybody starts using it. And then I start to hit the problem. And you'll notice most systems, they start to hit the problem when they hit scale. Then I realize that I'm getting a lot of calls and I'm not enough to address all of those calls myself. So then I start to think, and then I think, sure, let me get my wife also involved. So now this number actually has me and my wife, both of us sit with our diaries where the call gets routed to either one of us, whoever is free. And when I get a call, I just very quickly, if the person is asking me to take a reminder, I just take down that reminder, right? And when the person calls me back, I respond back with the reminder. Great. I have suddenly now doubled my capacity. If I was able to take 1,000 requests in a day before, now I can take 2,000 requests because I have my wife to help me as well. Very soon, I got my first unhappy customer. Mr. X calls me one day and says, hey, can you please remind me when is my flight? and I look through my diary and I realize I don't have an entry corresponding to Mr. X. And I tell Mr. X, hey, look, I don't have an entry corresponding to you. Mr. X seems very disappointed, very angry, and then disconnects the call. Now I start to think, what might have happened? Either Mr. X was delusional, or maybe there was a fault at my end. And then I see that there might have been a problem. It is possible when Mr. X wanted to store their reminder, they might have called my wife. And my wife would have stored this entry that, hey, X wants a reminder for a flight at 7 p.m. tomorrow. However, that entry is not with me because that call never came to me. However, when X wanted to understand when their flight was, they ended up calling me instead of my wife because they don't know. They only know this number 1234 1234. And I don't have that entry. And this is why X is very unhappy. This is what is called as consistency problem, data consistency problem, which is an end consumer might have stored some data with me, and when they ask me back, there is no guarantee that they will get the data back because it depends on where the request comes to. If the request comes to my wife, they'll get their data back. If the request comes to me, they'll not get the data back if my wife's diary has that entry. This is a big problem. If not solved, my company will die. So I start to think, and I come up with a solution. I say, hey, look, here is what we could do. When X calls me to say that, please note down that I have a flight tomorrow at, imagine 6 p.m. I'll note it down in my diary. I'll also tell my wife to note down this entry, which is also that tomorrow 6 p.m. flight. And only when both of us have written the entry in my diary, in their own diaries, then I return success. Then I tell Mr. X, I have noted down your entry. That way, there is guarantee that both of our diaries, my diary and my wife's diary, they'll have the exact same entries. Consistency of data. They'll have the exact same entries. And great, my consistency problem is solved. Now, when X calls any one of us, we can respond back with the right data points. Things were going great. One day, I again start to face a problem. One day, my wife calls in sick. She's not keeping well, so she's not in the office. What that means is that my wife, for the time being, is gone. For a day is gone. And at that very moment, another gentleman, Y, calls me and tells me to note down an entry. I say, okay, sure, what's your entry? And they tell me, you know what, I have a flight tomorrow at 3 p.m. I say, great, let me note it down. Let me, by the way, also go and tell my wife to note it down. Oh, by the way, my wife is not here. She can't note it down. And therefore, I'll have to tell Y that, hey, I can't note down your request. Your request actually has failed, which means for the entire day, I can't take in any new requests. That is a availability problem, which is my system is not available to take all kind of write requests. In the case of software systems, for example, like Facebook, you could think of Facebook saying that for an entire day or for an hour or for a few minutes, you can't make any new posts or you can't post any new photos on Facebook. That is an availability problem. So again, I'm very stressed. What do? I don't want my business to fail. So I think and I come up with another solution. I say, you know what? When my wife is not here, so I have my diary. And imagine my wife is not here. So I have written a bunch of entries. This new day comes. Whatever entries I get, Mr. X says to note down something, I'll note it down. When Mr. Y says to note down something, I'll note it down. And when my wife returns back, because I want both of our diaries to be identical, I tell her, look, you'll not take up any phone calls till you have noted down all of the additional entries that I made in the previous day. Or if she was gone for last 2 days, then in the previous 2 days. So you first note down all of the additional entries and then you start taking calls. And then my problem is solved. Now, because if X calls me and says that, please note down that I have a flight tomorrow at 8 p.m. Even if my wife is not in the office, I can still note down the entry. And therefore, I'm still available. Since my wife will come back and she'll actually catch up with whatever new entries are there in my diaries before answering any phone call. So we're also consistent, which is great. Things are going super good. And then comes another problem. One day, me and my wife, we both have fight and we stop talking to each other. So imagine I get a phone call, X says, hey, look, please note down, I have a flight tomorrow at 9 p.m. I can't note it down because I'm not able to talk to my wife. And if I note it down, then and tell X that, hey, look, I have noted down your entry, then my system becomes inconsistent, right? Because my diary has now different entries, my wife has different entries, and she's still taking calls. So when this network partition happens where I'm not able to talk to my wife or other systems, then I have to make a choice. Do I want to stay consistent or do I want to stay available? If I want to stay consistent, then if Mr. X calls me and says, please note down the entry, I will have to say, sorry, I can't. My system is down. It's not accepting any new write requests. If I want to stay available, then I can take down the entry, but then I become inconsistent. So if I choose consistency, then I become unavailable. If I choose availability, then I become inconsistent. And that is exactly the Cap's theorem. Cap's theorem says that if you have consistency, if you have availability, and if you have partition tolerance, then at a time you can only guarantee 2 out of these. You can't promise all 3 at the same time, which means when this network partition happens, I would have to choose between consistency and availability. I can't have both. That's the Cap theorem. Now I have 2 bonuses to add here. Most systems that are available and partition tolerant, which is called AP, A for availability, P for partitioning, C for consistency, right? Most systems that are AP can still make sure that they become eventually consistent. What does that mean? That means eventually my and my wife's diary, they have same entries. How do I make sure of that? Whenever we start talking again, we can exchange notes. Or maybe just imagine that there's a clerk here that I've hired who just takes up all of the new entries in the last 1 hour, tells me what those entries were, so I take those down. Also, by the way, asks me what were the entries that I made in the last 1 hour, goes back to my wife and tells, here are the new entries that were made in the last 1 hour. So there might be periods in between that I was inconsistent, but eventually we become consistent. So that is eventually consistency. There is one more extension to Cap theorem that was done very recently, actually not very recently, about 10 years back, which is called as PACELC theorem. And what this theorem states is that, hey, look, when network partition happens, when my systems can't talk to each other, then sure, you have to choose between availability or consistency. You can't have both. However, there are going to be cases when my systems can talk to each other, which means there is no network partition, which is else. So else, I have to choose between latency or consistency. I can't have both. If you notice, when I made this decision that to stay consistent, I will make sure that on every single call, I will make sure my wife also notes down the entry, and only then I return success. Then I'm actually waiting for my wife to note down that entry. My wife could be doing something else at that time. My wife could be answering some other call. And in that case, the entire request might end up taking a lot of time. So the latency could become high because I want consistency. However, if I was willing to let go of consistency, which is I wanted to say that, hey, look, I'll just note it down. And maybe, my wife could probably catch up later on. Then latency could stay really low. So then you would actually have a balance between latency and consistency when there is no network partition. So that's what PACELC theorem is, which is just an extension to the Cap theorem, because Cap theorem does not talk about latency. I hope that made sense to you, and I hope that was helpful. This Cap theorem is one of the most basic and one of the most useful theorems you'll come across when designing distributed systems. I'll keep doing more videos like this. If you like this video, please like the current video and subscribe to the channel. Thank you. Thank you so much.
If you are new to tech and you have recently heard the term caching and don't know what it means, then this video is for you. I was fortunate to see scale at Facebook. I was fortunate to be part of teams that build products that scale to millions of queries per second and billions of users. I'm here to share some of those learnings with you. If you like the content, please like the video and subscribe to the channel.
All right, so I'll try to explain caching as simple examples as possible. By the way, there is a bonus problem at the end of this video, so please do stay till the end of the video to look at the solution of that. All right, so let's imagine that you want to make milk tea. One obvious ingredient of milk tea is milk itself. And milk I find in most grocery stores, department stores that are around me. So one obvious way whenever I'm making milk tea is that I go to the department store, fetch milk from here, and then make my milk tea. This to and fro process, by the way, ends up taking a lot of time. However, one thing which strikes me is, by the way, I can buy a refrigerator. I can buy a fridge which stays in my house only, where I can buy few milk cartons at a time and I can store it here. And when I'm making a milk tea now, then as long as there is some milk present in the fridge, I can use it from here. If there is no milk present in the fridge, then I go to the department store and I buy the next set of cartons of milk. So what have I done in the process? I could still have gotten milk from department store. It's the same milk. However, I created this temporary storage which is close to me, which is much faster for me to be able to store those milk so that I can make my milk tea faster. Plus, then I have more motivation to make milk tea because I have it in my fridge. Very similarly, if you look at the design world, distributed systems world, you always have these systems that are looking for some or the other information, right? So machines talk to each other, they query for information. Imagine you load your Facebook profile page. That profile page would need to show your name, email ID, your friends, etc., etc. So for that, it would need a lot of information. So this machine would then ask for profile information for yours, which would be there in some other machine in the hard disk. And reading from hard disk is slow. If you would have noticed, when you transfer movies, etc., from your friend's laptop, those movies are written to your hard disk, and those hard disk writes are fairly slow. Very similarly, reading from the hard disk is also slow, especially if your data is lying somewhere you don't know where. So you'll have to search through the index to find where this profile information is and then fetch that data from there. However, if the same information was in RAM somehow, which is main memory, then accessing that would be faster. However, I mean, if we're talking about Facebook has so many people, so many profiles, all information cannot reside in RAM. It has to be in the hard disk, which is the same as me going to the department store every single time when I want to make milk tea. However, if I know that there are, let's say, certain profile pages that are fetched very often, that are more likely to be fetched than the other profile pages, then maybe I can create a fridge, a refrigerator, where I can store the information of these pages, so that when somebody asks for these pages, then I don't go to the departmental store, which is the hard disk in this case. Maybe I have that information in RAM or a faster memory access. I mean, let's not say RAM, some place where I can find that information faster than actually having to read from the hard disk of a different machine. That process is called caching. Caching is exactly what I did with my refrigerator to department store. It is exactly doing that to reduce the latency of fetching that information in some cases. A cache will never be as big as your total storage. There will always be cases when I run out of milk in my refrigerator, or when the information is not present in this fast storage. And that process, by the way, this is caching. And when I find data in my cache, it's called a hit. When I do not find the data because it is not present, therefore I'll have to go to the departmental store or go and read from this hard disk. That is called miss. So whenever you find data in the cache, it's a hit. You don't find it, it's a miss. That is caching. And caching is something, by the way, you encounter on a day-to-day basis. For example, you might have noticed that when you load a website for the first time, it's usually slower. But when you refresh, it loads faster. Sometimes when your internet is not working, you keep refreshing after a while, and eventually the website loads. Your internet doesn't get faster. That's not the reason why it loads. It loads because once, let's say there was an image on the website. Once that image has loaded, that means your browser has now gotten that carton of milk. So it caches that in its own memory. On your browser, on Chrome, it gets cached. So next time when you load the same website with the same image, the browser doesn't go and fetch the entire image from the other website. It only checks if it was the same image. If it was the same image, then it fetches it from its local memory, which means I don't have to go over that slow internet to fetch that image. And therefore, by using caching, I have significantly reduced the latency of fetching that data. That is caching with your browser. Systems within also do caching in various forms. One simple question I have. If you haven't seen my CAP theorem video, please go and see that, because this question is slightly based off that. Imagine you are building a very consistent system. You would want that if you're doing caching, then this cache data is exactly consistent and exactly the same as the data present in your hard disk for whatever entries it has. If you're building a consistent system and you're doing caching there when I ask you to update, how do you go about updating such a system? in the context of the departmental store and milk tea example. Let's say that you want your milk tea to always use the latest milk that is present in the department store, or always use the milk that is present in the department store. How do you validate that the milk that you have in fridge as of now is exactly the same milk that is present in department store? How do you do that? There is something called as well, actually, if you look at how you would do it, there are only two ways of doing it, right? One is when you tell me that, hey, here is new milk to restock your store with, or here is new data, right? Like, which is, let's say, and on my profile name, for some reason, my name changes. So whenever there is data pertaining to me that is being updated, it does not go directly to the hard disk. Imagine this is my hard disk or hard disk storage, and here is cache. Whenever this update operation comes, it goes through the cache. So first I check, is this entry present in the cache, which is my name, is my profile cached? If it is cached, then I first update the entry in the cache, and then I update the entry in the hard disk. And only then, when both of them have been updated, only then I return success. This is called write through cache, which means whenever new milk comes to the department store, it goes through me. It goes through my house. I do a verification, and only then I let the milk pass. That is write through cache. Or the other way could be that if the database is aware of where my caching system is, whenever there is a profile update, the database tells cache to throw away whatever information I have regarding my profile, because that is now out of date. And only once invalidation has been done, only this write has been done, invalidation has been done, only then you return success. Or in the context of, again, departmental stores as well as milk, let's say whenever my department stores gets a new kind of milk, they call me up and they say, hey, look, please throw away the milk that you have in your refrigerator. It is old now. We have a newer quality of milk. And that way I make sure I'm always cooking my milk tea with the newest quality of milk that I have in the market. That way I stay consistent.
Now let's start discussing about a client server architecture. So before jumping into the discussing about architecture, first we'll see what are the terminologies. Okay, so what is meant by client? So client might be user. Okay, so simply I will tell you with one example for better understanding. So one server might be some database or some backend thing. Okay, so you can consider client as working at front end. So let's say okay, let's take an example of CodeChef. Okay, so I have an CodeChef website. Okay, so I have logged in into using my credentials, and there will be something for search with username. Okay, so I want to know what are the ratings of my friend. Okay, so I will provide his particular username, right? Now, so what I will get all the details of his ratings and what are the contest histories and all. So what exactly happens behind this thing? Okay, so whenever you hit that submit button or search button, so it will go to a server. Okay, you can typically call it as a backend. So let's assume there are some DB over there, okay, which is storing all the informations of CodeChef users. Okay, so whenever you search for with that particular username, it will return you the details of that particular user. Okay, so here this particular, like, the web application which you are uh, using to send and request is called as a client side which you are using directly, and this particular part you are using indirectly. You don't know, like someone who is an 12th standard or 10th standard guy came and is searching something on Google. Okay, he don't know exactly what is happening behind that. He knows something like, if I enter like something, I will get something, that's it. Okay, so this is the back end side, so back end logic kind of stuff. Okay, so this is in simple what is client and server. Okay, we'll come to more details later. Okay, first we'll discuss
What is a before client server architecture? Before client server architecture. So before this, we used to have mainframe computers. We can call them as standalone systems. What does it mean? So let's say you have one computer and you have created some database by using any SQL SQL database, okay, on your local machine. Okay, so this is your system. Okay, so there is some SQL database you have created with some tables and all, and also you have created one a web page to access the SQL data, okay, database. So can I ask few questions here? Now it is in your system, so can your friend able to access that data which is residing on the database from his own system without having any connection? No, it is not possible, right? So that kind of systems are called as an standalone systems, where the data has been restricted to one particular system. So you might be the client and you are the owner. Okay, server is residing in your machine itself. Okay, so others are not allowed to use that particular server. Okay, so that is the before client server architecture came into exist. Now let's see what is a client server architecture. It is not new. Okay, hope we have discussed this in while telling the terminologies of client and server. So let's see in detail. Okay, so basically let's say you're at a client side and you will make some a request. Okay, you will make some a request to the server. What is a request? So a request can be anything. Let's say www.google.com can be one request, right? As I said earlier, searching with like entering one coach of username and expecting some all the details of that particular user. So here the request is, so search with the particular username, I want all the details. So that is one request, right? So this is a request. So what is this server side content? So it contains some DB, like databases. So tell me, is that always an data? Is that always an data? No, I don't think so. What might be? So it might be some calculations, logicals. Let's say you are using an EMI calculator applications. EMI calculator applications where you will be saying like I wanted to buy a home. Okay, so this is the amount I wanted, like 12 lakhs, I want 12 lakhs, and what will be the pay. Okay, what how much I need to pay. So per month, if the interest rate is 5% on the, and I'm willing to pay only, I would like to take the loan for 7 years. So is there any, do you think is there any DB involved here? No, but still it's a request, right? So I can say that there is a logic as well. So in server side I can say that both a DB and logic has been residing in particular machine. So here, after like whatever, if you have searched with user coach of username, it will go to database and it has to return something to the client, right? So it has to return the details of that particular user, right? So it will send some responses back to the client. Okay, so even if it is an logic side, like for this particular example, still it has to send some responses, right? So you have to pay monthly 23,000 kind of stuff. So even that is also one response. So this is how the actual client server look architecture looks like, and we oftenly call this as an two-tier architecture. Two-tier architecture. So why two-tier? So is there anything apart from a client side and server side? No, there is no other things involved. Okay, now let's see few things which were involved other things as well. Okay, let's say, so I have a client side and I have a, like I'm dividing the server side into the two parts. Okay, logical and DB. I know that sometimes I need not to go to DB. Okay, so I'm pretty much sure that I don't have a work with a DB always. So what I will do, so I will go to simply to logic, and I will check whether it's a logical based or it requires DB. So if it is a logical based, what I will do, I will solve the problem here itself. Okay, if it is a logic based DB involved, I would go here. Okay, so this kind of things being called as a 3-tier architecture. So 1 2 3 3-tier. So there is something like a entire architecture as well. Entire architecture, what does it mean? So let's say you have a client and you are using some load balancers to process your request to different servers. Okay, so let's say you might have one server, but there might exist of different clients. Okay, so n number of clients, no guarantee, right? Always. So do you think only one person can at a time can search in and Google? No. Okay, so many people, some billions of people used to search at a time. So how they are processing your requests? So if they have multiple servers, they will use load balancers to divide your request to and process your request to multiple servers at a time, to feel that you are in an, like you are the alone, you are using that particular system. Okay, so and so instead of going to directly to the server, let's say you have a cache, you have a cache memory. What I will do for the first time, I will request. Okay, so it will process to the server, like it will go to the first, go to the cache memory, and it will search whether whatever I have requested is there in cache memory or not. Okay, so if it is presented, if it is there in cache memory, it will simply return from cache memory itself. Okay, it won't go to the server, just because of the fact that I have found, okay, I have response for your request. So if it is not there in cache, what it will do, it will go to server and it will take that response. Instead of going directly to the client, it will go to the cache first, okay, cache memory, and it will put a replica or copy of that response in a cache memory, then it will return to client. Okay, so here this like this, so I have simply used a load balancers and cache here. So there might be other things will also exist while designing complex systems. Okay, so in that situations you can call it as entire architecture. Okay, yeah, so yeah, let's move on. So the next part is thick clients. Clients have been divided into thick clients and thin clients. What are they? Who are they? Right, you might have that question. Let's say, so a thick client is or something. Okay, let's say, hope you have a client side rendering and a server side rendering. What does it mean? So basically, so do you think all the calculations you do will go to the server? No. Let's say I have simply developed an calculator app. Okay, so I will enter two values, 2 plus 3. Okay, do you think it will go to the server and it will do some logic and it will come back to a result? No. So I can handle this in my code base only, like at the client side as well. So that kind of systems will call as a thick clients. Okay, who does their work at the client side only. So some of the famous example, like, so we use a lot of things in our day-to-day life. So fewer Outlook and Gtalk, Google Talk, and also some online trading portals as well. Like it involves a lot of calculations, right? So yeah, so that is about thick clients. Now we'll talk about thin clients. So it's quite opposite to the thick clients. Okay, so in thick clients we are rendering at the client side. So in thin clients we go to the server and will process our request in server and will get some response for a response. So that is a thin clients. We can consider anything like simply a school database or college database. Okay, so where if you are searching for an employee or any student, okay, student, so your request has to go to the server side and it has to get all the details. Even in the in very first example that we have discussed, CodeChef application, so even it has to go to the CodeChef database and it has to process that request, so it has to return that. That's it.